Bye. Device.
You're sitting on a bench, watching basketball games. You can scratch it though. Because I think the train was like 4 AM. Yeah, it's like that. Brutal.
Oh man, it's a chaos machine.
Sharing.
I'm not sure.
I don't even see it. I should get better at like reading.
I think he's coming down. I'll go.
Nice, if he's coming down.
Yeah.
Like other people
State of work.
Stand close to this, and these ones are on.
What about the slides?
And he'll just start. So these ones are just for Q&A, he'll switch them on when he sees us doing Q&A, I assume.
Okay,
I mean,
after the presentation.
just go now, we take questions.
Yeah.
Okay.
Okay, start. Yeah. So welcome everybody, especially people here, people online, if they can hear me. I hope they can. And thank you for coming to this meeting that took a lot of organizing. Thanks to the organizers, Greg, Anne, and the ones who are not here, John and Vivian, was probably running. And just to give you a little information, first of all, Wi-Fi password. The Wi-Fi is the public Geological Society password, Wi-Fi, and the password is sediment, all lowercase. And you will need it because Naren is gonna do a poll. So if you can log in now so you don't waste time doing his talk, that would be great. So a little overview of our sessions today. After I finish speaking, we'll have the first session with searches. And each session will have an introductory talk of about 10 minutes, then some panelists sitting here and giving a little overview plus questions to the audience, and we can have a quite long discussion afterwards. Then we'll have some breaks, we'll have coffee. I guess everybody knows that lunch will unfortunately not be here, even if we tried a lot to get some funding. So everybody has to look for their own lunch, and we sent some recommendations. I hope they reached you. And yeah, the second session will be on parameter estimation, the third one on next generation detectors. A few announcements, of course, fire exits, follow the science. In case of fire, we hope nothing like that happens, but you never know. And I guess that's it. If you don't want to appear in pictures, because we were asked to get some pictures around, please let us know, or wave your hands when someone is taking a picture, and no, shout loud. And that's it, I guess. If I can ask the first panelists to come over and take their places, and I leave the floor to Greg, who's gonna share the session.
So saying only these mics work?
Yeah, they will put them on later for the question. You only have
Okay, wonderful. Okay, so the way these sessions are going to work, we're going to have Sparkler slides at the start, and then we're going to have some slides from the panel. So we have first Sparkler slide right now. I guess I press next.
I don't know if you're allowed.
Okay, so here's our first Sparkler slide. And do we have Naya online, I think?
Yeah, can you folks hear me and see me?
Yeah, we can hear you. So please take it away.
All right. Hi, everyone. My name is Naya Raza, and I'm a PhD student at McGill University in Canada. And today I wanted to briefly mention the GeoBlue Skynet multi-classifier. So the LVK released a rapid public alerts for candidate gravitational wave events, which includes information like the sky localization maps for follow-up observations. But some of these events can be false alarms, known as glitches, or not even be, even if they are astrophysical, might not have an electromagnetic counterpart. And so we developed GeoBlue Skynet Multi as this deep learning classifier as a complementary tool that uses only the localization information from these public alerts to try to predict the type of event between glitches or BPH, NSBH, or BNS. And we've recently updated the model, simplified the architecture considerably, and optimized it for O4 events. And it's performing well, but I wanted to suggest or highlight two topics, two challenges that we've come across for further discussion, which is the distribution shift we see between simulated events that we use for training versus real world events, including neutron star events, which are very few, and interpretability of these deep learning black box models and how we can build more trust into them. Thank you.
Thank you very much, Naya. So this is obviously a Sparkler for a poster. Is there a physical poster here? There's no physical poster, but of course, if you're interested in this, please do get in contact with Naya. And I would guess, thank you for joining us very early in the morning. Very much appreciated.
Yeah, looking forward to it.
So now we're going to move on to our overview. Actually, sorry, first let me just introduce the panel and then we'll go through the slides. So we have Narayan Nagarajan, who is from the University of Glasgow, Patrick Sutton from the University of Cardiff, Joe Bailey from the University of Glasgow, and Vasilios, I'm going to check it, Skliris? Thank you, my apologies, from the University of Cardiff. So we've ended up with a very Cardiff-Glasgow mix here, for better or for worse. So the way this is going to run, we're going to have a 10-minute overview from Narayan first, and then a 1-minute slide from each of the panelists, and then we'll move to the discussion. So let me pass over to Narayan. There's a laser pointer for you. Yeah, and then just those to go next.
Okay. Hello, everyone. I'm Narayan Nagarajan. I'm a PhD student at the University of Glasgow. So I was told to give a brief overview of gravitational wave searches and for using machine learning. So I think there's a lot of work and I can't do justice to everything. So I'm mainly going to be talking about current issues with machine learning and that are mostly common with many different kinds of using machine learning within the search field. So yeah, basic diagram of the entire workflow of starting from the interferometers, getting the data and everything. So I think machine learning is sort of used almost everywhere in this block. And what I'm mainly be focusing on is search stuff over there, and there'll be panel sessions and other ones later on. So I just wanted to see how much work there was, and I just went through one review paper on this, and there was so much work. And this is kind of why I said I can't do justice to all the work that people have been doing. And if I just started to give an overview of the entire field, and there are so many different issues that people have to deal with in different areas of the field, and they're completely different from one another, that talking about all of them is pretty difficult. So I'm just going to put this up there and say that these are some of the things that's been done, and there are other topics that I've also left out of this, like detection of overlapping gravitational waves, Emery detection, and exotic sources and other things. There were many other papers that I actually didn't put up on there, but there you go. But yeah, so a little bit about simple machine learning stuff. So what I have up there, so I'm an expert mostly on model transient searches using machine learning. And so I'll be talking about things from the perspective of this, but I'll be talking about generic machine learning issues, and you can sort of extrapolate to your own field or to something different. So usually with machine learning training, you have some noise class, signal class, some data that you're curating and making, throw some data augmentation in there, do some filtering, and do a little bit of whitening, PSD estimation and whitening. Then sometimes people have data transforms where you move from the time domain to either the frequency domain or time frequency domain. And then generally, some people have reversible compression stuff so that you compress your data so that the data that the machine learning model is dealing with is not too much. Then you throw it into a machine learning model and it somehow learns, and you get to do detection stuff with it. And during the testing phase, you could also have like a noise handling thing on the side where you're doing glitch vetoes and noise subtraction and many different things. Maybe also using machine learning. Okay. So moving on to the main stuff. So I'll mainly just be going through generic issues. So these are some of the issues that I won't be going through them in too much detail either, because I have about 10 minutes. And there'll be a little more for the poll. So this is kind of part of the poll, but there'll be a little bit more in the poll as well, which I'll introduce later on. But the 4 things that I'll be talking about is interpretability of results, compute data efficiency, extrapolation capability, and evaluation metrics. Okay, so first one, interpretability of results. I'm kind of throwing out questions on sort of both sides of things to see where this goes, to sort of create a divide if possible. The point here, the first one is interpretability as a positive thing. So interpretability leads to better solutions. It gives you better understanding. It gives you more confidence, which is why it's really needed. And some of the things that it helps you with is some signals, for example, might not be learned well by the machine learning model, and you want to know where that is. And it might struggle with certain types of noise. You want to know what that is so that you mitigate them properly. And there's incorrect feature attribution, which is, if you've not heard of it before, it's some parts of the signal where not some parts of the data where it shouldn't really be focusing. It kind of focuses on unintentionally, not unintentionally, because of the training data. One classic example of that is, I think there was a work a long time back in the medical field where people were looking at skin issues, and every time they had an image of a skin issue, they kept a ruler on the side. And what the machine learning model did was, instead of learning the feature of the skin issue, it just said, if there's a ruler, there's a skin issue, which is incorrect feature attribution. Things like that. And in terms of gravitational waves, there's this paper, the Magic Bullet paper. It's a really nice paper on that goes into some details about this and other issues as well. And there's the 4th point, which is outer distribution stuff with machine learning. So what is outer distribution? So in distribution is if you provided some data, then the features of all of the data put together is in the distribution, in the training distribution of the model. And so I'm mainly just talking about supervised machine learning here, and anything outside of the distribution is out of distribution, obviously. And so what does that mean in terms of gravitational waves? So with signals, if you have a parameterized model, then anything out of the bounds is out of distribution. But if you think about non-parameterized stuff, then what exactly is out of distribution there? How do you take care of those? And especially with noise in every single case, what exactly is out of distribution, and noise, what exactly is in distribution? How do you actually quantify that? So if you learn something about noise, then, and if there's a noise that's completely unseen, and does it have features that is completely outside of what you trained on? And if it does, how does the model handle it? And how do you know anything about it? And the other side of interpretability is over there, which is if I can create a model that where, let's say I do an injection study on like 1 year of data, provided a huge number of realistic signals and in real noise, and it can detect them at a false alarm rate that is similar to what classical methods do. If I do that, then is interpretability required then? If I show that the model works well in real data and it can compare well with classical methods, does it really need interpretability? And the next thing that many people mention when it comes to interpretability is sort of incorrect classification. So that doesn't really make too much sense here in terms of detection because you're talking about a false alarm rate. But what I mean there is sort of signals found at really high false alarm rates and noise found at really low false alarm rates. So if a really well-trained model on lots and lots of real noise is still making a mistake like that, then one of the questions that you could also ask is, do classical methods also struggle with it? So you have waveform consistency tests and glitch filters. Do those methods also struggle with some those types of noise? But yeah, those are two sides of things. And a little bit about interpretability on the positive side. So one of the things that I was working on, that's a shameless plug, my paper, which is currently on PNP. It'll be on arXiv next week. But mainly what I was working on was identifying and mitigating biases. And one of the biases here is spectral bias that I'll be talking about a little bit. And what that is, the plot that you're seeing there is on the x-axis is all frequency, and the y-axis is training iteration. So for different frequencies, what you can, and the color bar is if you're at 1, which is the lighter color, the model, it means that the model is trained really well and can understand that frequency properly. And if it's black, it doesn't understand much. And what you're seeing there is along the training iteration, different frequencies are learned differently. And for example, low frequencies are learned pretty quickly, and they're pretty stable throughout the training process, and it's fine. Higher frequencies, they're not learned that well, and it's still unstable even after like 40, 50,000 epochs of training. And what they're using here is just sine waves at constant signal duration, different frequencies. And what that shows in terms of gravitational waves is that, for example, if you take a low chirp mass gravitation wave, then it would typically merge at higher frequencies, higher ISCO frequencies compared to high chirp mass gravitation waves, meaning that low chirp mass gravitation waves will be unfairly, the model will be biased against it a little bit compared to high chirp mass gravitation waves. And that's an issue. And it's not just between different gravitational waves, but also within a wave. Within, you're looking at a chirp, so different parts of the chirp will be learned differently during the training process, which is also bad. And this is one of the biases, but in my paper, I talk about 10 other biases. It's a long paper, but and also mitigation tactics for those. But yeah, things like this could be useful as well. And another form of interpretability could be another kind of perspective of interpretability. This is just something I ran yesterday, so don't mind the really bad looking plot. So what that is I took 2 models, and with one model, I gave it a bunch of different signals, and I gave it some easy pieces of noise on the side for it to classify against. And the other model, the one on the right, I gave it difficult signals, so lots of glitches, lots of not well-behaved PSDs and stuff. And what you see is that the one on the left, so beyond a certain threshold in SNR, so first to explain the plot a little bit, the x-axis is network optimal SNR, and the y-axis is the ranking statistics, some output from the network. And what you see on the left is that beyond a threshold in SNR, beyond a threshold in network optimal SNR, the network ranking statistic is exactly the same, almost exactly the same, meaning that it doesn't care between a signal that is SNR 10 and SNR 14. It puts them pretty much in the same place. What that means is if you have a difficult piece of noise there, and if you test it on a difficult piece of noise, it's going to place it somewhere, let's say close to SNR 10, then your false alarm rate at the lower region will completely go off. It'll be really, really bad. So if you're not training on it properly, then you're not going to get something that works well. But if you do it on real noise, for example, not real noise, but difficult noise, for example, I got this, where you get a lot of difficult examples, and you're kind of forcing it to learn to kind of understand that scaling operation of SNR a bit better. So in terms of interpretability, so lots of people talk about like looking at subnetworks and activation patterns and things like that. But Is that something that we're looking for, or things like this, where you just look at the output of the network and try to interpret something out of it? Is this interpretability, or are we looking at other forms of interpretability? So it's things like that. How much time do I have left? Okay, I'll go quickly then. Compute data efficiency. So I won't be talking about 2 and 3, just the one. So if you take LSTMs versus transformers, for example, LSTMs, typically you can't do things in parallel. Transformers you can, meaning that you have computational efficiency with one and not with the other. So things like this. So if you choose different architectures, different ways of handling data, then you have more computational efficiency with one rather than the other. There are some advantages for that. I won't be talking about that too much. So data efficiency, this one is pretty interesting. So if you've heard of equivariance before, I'll be talking a little bit about that. What I've shown here is something called translational equivariance with CNNs, fully convolutional neural networks, and just focus on, let's say, this bit or this bit. Let's take the butterfly, for example. So if I give an image of a butterfly in a certain location, it creates a feature map. It creates a CNN feature map, something that looks like that, say. And so one of the main advantages of the CNNs, and the reason that it became a huge thing in the 2000s, was mainly because of this equivariance property. So it creates a feature map like that. But then if you were to move that butterfly to a different location, it creates pretty much the same feature map, but in just a different location. It's also translated in the same way. So that kind of concept of, if you change the image in a certain way, give it a translation operation, then the feature map is also transformed in the same way. That is equivariance, and this is translational, so that's translational equivariance. So the advantage of that is that, for example, instead of training your model where you place the butterfly in every single location, and then just to make sure that if you were to provide an unseen image, the model is going to kind of going to say that what I'm looking at is indeed a butterfly. People usually do that in forms of data augmentation, where you can rotate an image, you can translate things and different things like that. But if you had something like this, where you have translation equivariance, you could simply train it on, say, a really limited amount of butterfly positions. And in the end, the model kind of innately is capable of understanding that if you put it in a different location, it's still the same butterfly and it's still the same features. So things like that, and this in terms of gravitational waves would be, if you have gravitational wave somewhere here, and then if you change the time of coalescence to a different location within the same sample, then it's still the same gravitational wave, it's not something different. So that's true for fully convolutional neural networks, but and there are different types of equivariances and things. I won't be going about that too much, but that gives you some understanding of what data augmentation actually is. But yeah, a little bit of extrapolation capabilities. So I took PSDs from O3, for example. So the blue ones and the orange ones are let's say the training data PSDs, and if I have the testing data PSDs to be yellow and purple over here for H1 and L1, would that be an issue? Will that cause issues? Because I'm training on kind of well-behaved PSDs for H1 over there with the blue, but if I provide yellow for the testing, would it behave in a worse way? That's something we have to think about. And even if it does behave in a worse way, even if we say that it can extrapolate a little bit, to what extent? So if you go even above that, is it going to work? Is it going to be worse? Is it a continuous thing, or is it just going to abruptly just be bad? This is the last slide. And that's evaluation metrics. So initially I spoke a little bit about biases as well. So here, this is one of the papers that came out a couple of years back with a mock data challenge and BBH detection and stuff. So there they use an evaluation metric over there, the sensitive volume, the sensitive distance, but that is something that is proportional to chirp mass, for example. And initially I mentioned something when I spoke about biases, that you can be biased against certain things within the training distribution. So if you have a classical method that is acting on the whole distribution, and if you have a machine learning method that's biased against something and in turn operating on a narrow distribution, then you're not doing as much background estimation. So you're pretty much kind of going to be finding more signals in the region that you're looking at. So say you're biased against low chirp mass signals, and you're finding a lot more high chirp mass signals than classical methods in that particular narrow region, then what happens is, because of scaling due to chirp mass, you're just going to end up with a really big sensitive volume comparatively. Doesn't necessarily mean that the machine learning model is performing better than classical methods because you're using an evaluation metric like this. And you can see like the top two results over there, ARIES-GW and SAGE. SAGE is my work, and ARIES-GW is another work. So both of them seem to be completely above by CBC till about fault tolerance rate of 1 a month. But if you actually look at the plots of the histograms, it doesn't really find as many signals as SPICE-CBC does, and those are kind of the issues here. And that's pretty much it. And there are many other issues, but I have 10 minutes and I'm done. Yeah.
Excellent. Thank you for that overview of some of the topics. So now what we're going to do, I think before we go to questions, let's go through some of the slides from the panel. So we have, firstly, people's names up here. And then we have, firstly, Vasilis. I think are we in the right order?
Yeah.
And that mic's on, so please take it away. A minute or so.
Can you hear me? Good. All right. So yeah, my main problems come from working practically on the Emily pipeline, which is the main thing we developed in Cardiff, and my experience comes from all this. So all these years that I was working with machine learning and trying to figure out an unmodeled search for low latency. So it's not, we don't try to exclude outliers hours later. We try to do it on the fly. Is it worth to have like a big model that finds them all? Is it like, do we want to have like a really big model that it's uninterpretable at the end and has a better result? It can be generalized. Other things about latency. So machine learning, one big thing of machine learning is making things faster than other things and computationally less expensive. But how fast is enough? Is fast enough? Like where is this limit? Do we need to be as fast as possible, or we can find a way to balance speed over efficiency according to what we want to see? And inspired from the first bullet point, I would say is that even if you train a model, it will have probably some many searches have this already. Like WB, for example, has the same thing. They have bins where the low frequency triggers are separated from the high frequency triggers. Is this a good practice? Like we realized with Emily too that we have specific glitches that are really problematic, and we try to exclude them. And I'm trying to think like, is this like the way we want to go ahead? Because low frequency triggers that are really, really narrow could be real signals at some point. So is this like a good practice? So it's like more like a general question I have around this time. Thank you.
Excellent. Thank you. So next up is Narayan.
Yeah. What I've shown here is kind of a bigger superset of what I spoke about before. Lots of issues, kind of like interpretability of results, compute data efficiency, that are other types of efficiency as well, extrapolation, having a consensus on data handling, something that I didn't mention before. So with machine learning, I would say that there are way too many pipelines. And so when it comes to actually using this in the LBK, what exactly happens? Do we have a consensus on certain things that are going to be done similarly between different pipelines, or is every pipeline going to be different? If every single pipeline is different, then you need experts on every single pipeline in order to actually handle them and handle issues and troubleshooting and everything in low latency. And so if you could put a lot of things that are, if you take too much of it and you say that all of this has to be constrained, all of the pipelines have to do this particular thing, then that's also an issue, because then that doesn't allow like particular machine learning methods to do things in a different way to get different results, different types of analysis. So where do you draw the line? And accelerating classical methods using machine learning, that's also a thing that there's lots of papers on this. So is that something we focus on? So in that case, there is some level of lack of interpretability with the machine learning bit, but then towards the end, you're using a classical method, so you have a complete understanding of what that does. So is that something that's better? Or the last point, which is evaluation metrics, which I think I mentioned already. And do we, for example, we take care of biases? Do we have to do this? And that's also something that you don't have to take care of when you're thinking of applying machine learning to classical methods, because towards the end, you're just accelerating the classical method and you just have an evaluation metric. But with machine learning, you have to think of whole new evaluation metrics. And there is just so many ways to make evaluation metrics for machine learning that where do you stop? What do you do? Things like that. So I just wanted to rank this at some point. I guess after we go through all the different questions, what you can do is just go on menti.com and you can put the number in, So can we go to can we come back to the slide after? all the
Yeah,
segments
I
are done?
can. Yes, if people want to go to it now, you can take a photo. If not, then we'll come back to this so people can do it with. Okay, so next up we have Patrick.
I'm gonna have to stand up, otherwise I'll crack my neck.
And the laser there.
Okay, thank you. Hi. So my machine learning experience over the last few years have actually been working with Facility to get an unmodeled transient search working for LIGO Virgo Kagra. I think it's worth pointing out, it's been about 7 or 8 years since the George and Huerta paper, the first one on convolutional neural networks for gravitational wave detection was published. And in those 7 or 8 years, LIGO Virgo Kagra have deployed 0 machine learning based pipelines to detect binary mergers. So I think it's interesting to ask, why is that? So I've just put a couple of thoughts of basic, step back pros and cons here. So one of the big advantages of machine learning we're all aware of is how quick there. Once you've trained your model, it's very, very fast to evaluate, the pump new data through the model and get an evaluation of whether you detected something or not. So that's a natural application for low latency analyses, which is the focus of a lot of us here. And the other advantage, of course, is that machine learning learns the patterns in the data by itself. So you can train it on glitch populations, signal populations, et cetera. You don't really need to understand what those signals are in principle or what those glitches are doing in principle, as long as you've got enough data. But then that brings us to the cons, which I put here. The machine learning algorithm figures out the patterns in the data by itself. That's also a problem because it means you don't necessarily understand what your algorithm is doing. It goes back to the interpretability issue that Naren brought up several times. So that's one real issue, right? You deploy your algorithm on the data and you get some weird results coming out. And then what does that mean? What do you have to do to fix it? That's a real problem, I think, for getting these detection searches to work. And then the last one is that the machine learning algorithm figures out the patterns in the data. And I stress patterns in that, and these are basically interpolation or averaging algorithms in some sense, pattern recognition. So I think by construction, they tend to be very, very good at getting 99.9% of the identifications correct. That's kind of a standard good performance. But if you're correct 99.9% of the time when you're analyzing LIGO Virgo data, say you're analyzing in 1 second chunks for short signals, that means you're going to be pumping out 3 or 4 false alarms per hour. And you can't tell people with telescopes to waste their time 3 or 4 times per hour following stuff that's junk. You need to be correct about 9 nines accuracy, sort of once per year level false alarm, right? And that is not a natural accuracy level, I think, for most algorithms that are deployed in the wider machine learning world. So these are just some of the things we have to overcome with making this work.
Thank you, Patrick. I'm sure the questions are brewing in the audience, but we have one last slide to get to. So Joe, please take it away.
Yeah, so I thought I'd just put on a different kind of search, different from all the CBC and short duration things, which is just long duration searches. So for ground-based detectors, this would be like isolated neutron stars being the big one that we look for, and how machine learning can be helpful for that. So the problem with these is that there's a lot of data to search through, like the entire year's whole observing run probably. And the parameter space is really large. And certainly over that duration, in a traditional search, you'd need lots and lots of templates because you're really well resolved at that source. And this is one thing machine learning, up to now at least, really struggles with, which is, trying to retain that information over a long amount of time, and detecting that to a similar level. I think there's been some examples of detecting it up to 10 days at the minute, and match filtering, but doing this over long durations is much harder. And this probably has parallels to future detectors as well, where you need a lot more data, although they'll be signal dominated, so they're a little bit different. Yeah, so I just thought I'd put up that as one question there. How do we do that?
Excellent question. Okay, thanks to the panel, we've managed to stay mainly on time. We now have 40 odd minutes or so for discussion, which is the main purpose here. Before we get into that, let me just put this back up. So if you want to go on menti.com, and I think it's for people to do sort of during this, right? And then we can maybe look at the results or something.
Yeah, we can look at the results. So
Maybe at the
after people have done, we can sort of look at the results after people have done.
Excellent. Okay, so with that, I'll leave that up there so people can take a look. But now is the time for questions or comments. It doesn't have to be a question. I open the floor. Who wants to go?
About the polls, I forgot. About the polls, there's it's ranking based on impact and effort needed in the next decade, for example. So how much effort do you need to put in order to sort of get to a pretty good level, and also how much impact does it have on the research community, do you think, in the next 10 years? It's ranking based on that on a scale of 1 to 10.
Okay, I don't see any hands up, so I'm going to get us started. I would like the panel to answer. So Patrick pointed out, we have no pipelines that are looking for compact binary coalescences that are in so production, if you like, in the LBK. We, of course, now do have things looking for short duration, burst searches, and work on CWs. But given that we need a lot of trust in the results, will we ever be able to firmly detect a different source class that we've not seen before with a machine learning pipeline first? Or will we always need some kind of classical understanding of what the system is? Vasilis?
Yeah. So this is it's a very interesting problem that every, I think, observing ground comes up. Like, what if we find the burst? What's happening? And if we get any signal that if you get any trigger where burst pipelines fire up and CPC pipelines might fire up, or there's like a conflict of confidence, the probability tells you it's probably CPC. Like, to not even think about it. Don't get excited. I get excited anyway. But I think even if we find something, we need maybe to define a way to add the probability of finding a burst to what we already have, like a P astra for bursts. Sorry, I forgot the question.
So I guess the question is, we have machine learning pipelines across the board. Right now, I guess my opinion is, if someone was running a machine learning pipeline for CBCs, I would be prepared to believe its outputs in some sense, because I have a traditional pipeline to compare against and validate on fresh data, right? But when I see the outputs from, let's say there's a CW pipeline or something like that, and the only thing that finds it is the machine learning pipeline, I would have serious questions, right? How do we address that? I'm going to go to Joe, and then I can see hand up from Ian.
I mean, I feel at some level you're always going to need some sort of follow-up to that. If it's an unknown source, for example,
yeah,
you're always going to need a follow-up and some understanding of that. But the machine learning could be the only thing that could highlight that there's something there, right? But that on its own is probably not enough in that example.
Is that unanimous from the panel, that you think that like a hybrid approach is always going to be the case? We'll never trust machine learning entirely? Would anyone stick their neck out and say I would?
I'd never say never, but right now I think I would agree that you'd want a hybrid. You'd want confirmation by something else.
Yeah, I agree with Patrick.
So Ian had a hand up first, and then.
I mean, I actually think you're being too narrow and perhaps too unfair to machine learning pipelines. Perhaps the question I would ask is, if CWB sees an event on its own, are you going to believe it's real? Because I know full well what my answer is if I don't look at the Q-scan and see it. And actually, you could even draw that back for 1509-14, had we looked at the data and not, the reason we all knew was because we could see it, right? There is no doubt in anyone's head. But if that were SNR 10 and you couldn't see it, didn't matter that GSDLR and PyCBC said 5 or 82 or 4 sigma, we wouldn't have been believed at that point. We're believed now because we've seen so many events. So I don't think it's necessarily a machine learning question, because frankly, I'm not going to trust the non-machine learning burst pipeline when it claims. I mean, I don't, because this has happened a few times already, and they've all been wrong, right? So not only that, I've now got a prior telling me that whenever it claims an event on its own, it's wrong, right?
Some of us don't trust all the branch filter pipelines either.
What we're learning is we're all a bunch of suspicious people. Probably why we're in this.
We've grown up in that community. Though, right?
If you can chat on the mic, just because there's people online. But please do. Continue. It's a panel. It's a discussion.
I mean, we've grown up in a community. I mean, especially those of us that are graying now. We've grown up in a community of being cynical and being challenged because no one ever believed us, and we had this history. I mean, I think it affects gravitational waves sociologically a lot more than other fields where your gravitational lens, whatever. I'm 90% sure it's real. That's fine. I'll write a Nature paper. Right? That doesn't fly in our field.
Narayan, did you want to? No. Okay. Is there? Let me just see. Is there other questions that people want to move on to? There's a few. So I'm going to say this question. We'll draw a line under it. There's a hand up here. Oh, please go ahead.
Just that if you're saying you want to be able to look at the data and see the pattern yourself, regardless of the statistics. Does that not come back then to what Patrick was saying, where the thing with machine learning is that we don't necessarily know the pattern we're looking for. So it's more likely that we're going to get a detection where we don't know what the pattern should look like in the data that we should be looking for to verify it. So in that sense, maybe it is more likely that with the machine learning pipeline, we're going to get a detection that we don't trust because we don't have any way of verifying it, because we don't really understand what's happening like under the hood in the algorithm.
The panel wanna. That's it.
Can I just?
Yeah.
I think we can answer. I think that especially for best cases, it will until we if we will be able to say we've solved for the best only if it's like loud enough, like the first BMS detection. That's so profound that it's a true thing, and everybody will be confident. You know what? At every low trigger burst we see from now on, it might actually be a real thing, and it's not just at least people argue that's the true thing. So to get that confidence, machine learning or not, I think you need something very, very obviously burst, and not low frequency, might be high mass CBC. But I think that's my opinion. Okay.
There's a hand up around here.
I have a sort of related question for Joe, not in terms of bursts, but continuous gravitational waves. So how important do you think is it actually that we understand how these sources are, for example, made in or like signals made in isolated neutron stars? So how to actually detect your signal, how good of an understanding do you think you need if I were to give you an actual like model on how to like make these things in terms of like oscillations inside the neutron star or like a glitch? Pulse or spin-up glitch that produces the signal. How good do you think these need to be for you to actually be able to help you with this or detecting a long-term signal?
So in terms of how good does the model of the source
Or like,
be?
does it not matter? And you will at some point basically just say, okay, look, I've got this continuous gravitational wave. I know this is one. Now do something with it. Or do we have to talk to each other more to actually be able for you to detect these?
So I think in terms of if we were detecting this with machine learning, it would be we've found something, then we'll go and speak to you and say, right, how does this fit? How do we fit this to a model that you have right already? In terms of like more traditional approaches, you need the model to be pretty accurate for CW searches because they're so well resolved. So if you're a bit off, you're going to lose a lot of power throughout your search, which I guess is a thing machine learning could mitigate a little bit because it might be able to, get around those problems slightly. But ultimately, yeah, they'll need a lot of communication with the model as well to understand something about the neutron star inevitably. But we haven't detected anything yet. So really detection is the first step and then moving on from there.
If I can, something I forgot earlier, when people from the audience ask questions, if you could just say your name or something, just so that people online know who's talking, that would be helpful. Hong.
Hi, my name is Hong. I have a comment on the previous question, and I have a separate question. So I would naively think, can we, like, if a detection is only detected by a machine learning pipeline, is it possible that we can use parameter estimation to check, suppose it's BBH or whatever, to check whether it makes sense? Then we may have a clue, or we can check against the classical pipeline. Classical detection pipeline, or maybe you said that, well, classical pipeline doesn't. Yeah, can we check with the parameter estimation results to determine?
If I can, I'll take the chair's prerogative to answer. No, because in parameter estimation, you're calculating a posterior, and on the right-hand side of your conditional probability is a signal. So you're assuming that there is a signal. So it can certainly, tell you something about the thing itself, but you can't get a confident statement out of that because you're assuming inherently that it is a real signal. So it can tell you something like, oh, this, this looks glitch-like. We often use that, right, as an example. But if you want the significance of the candidate, to my knowledge, there is no other way than a search. That's the job of a search pipeline.
Okay, thanks. Yeah, I'm just saying that if we use parameter estimation to check that time, the data around that time, we can have some posterior. If it totally doesn't make sense, then it's not.
Yeah.
If it makes some sense, then we might want to
It can build some confidence, but it can't change your statement about your significance.
Okay.
If you can do that, come and talk to the search people, because we'll fold that right into the search. I mean, if there's something you can highlight.
There's some information that people know from their posteriors that you look for, then, you know, let's try and quantify that, and, you know, we'll put that in searches and run it up front. You know, if there is information that we're not doing, then we're very willing to try and get that in, because we've got to beat GSD-Lat.
Can I ask my question now?
Please go ahead.
So suppose we determine what efforts we want to put in. Do we have a plan how we organize the efforts? Because in the past, like, people developed many pipelines, and then we work separately, and then we converge into one pipeline. Do we have, like, based on the experience, do we have a plan to do this beforehand this time?
There's no official machine learning group in the LVK. So if we have one, it'll be something that people could actually go there and discuss and come to a consensus on different things. But until we have something like that. But also having a machine learning group is pretty difficult, because then if it's an overarching machine learning group, that'll have a lot of overlap with everything. So maybe a machine learning search group might be helpful, but I'm not sure.
I should probably comment on this. So so speaking strictly within the Lycos Virgo collaborations, of course, you're correct. There's a long history of many teams independently developing many different search pipelines to do the various burst and CBC merger searches. There is a drive over the last few years to try to not exactly restrict, but to provide more rigorous justification for how many searches you want to run and how many searches you want to publish results on. And so there is a drive towards sort of convergence in the collaboration, but it's early stages yet. And no, there is no formal plan for, say, you know, converging to, say, a single master pipeline for binaries, for example. There's just there is a tendency or direction of travel at the moment, but nothing formal.
Thank you.
Yeah, again, speaking for LVK, the cargo collaboration, there's a name for what you described. We call it many times fragmentation of effort, especially for machine learning searches. Many people independently making algorithms, showing a proof of concept, and then stopping there, because making a paper out of this and stopping there, because it is a lot of work to go further. And it's not a simple thing to generalize. We had this discussion has been many times around. There is some kind of like machine learning group. You can't say machine learning group, really. It's more like people coming discussing these things in some calls. But I think it will be quite difficult until you have a successful example where people can actually try to improve, like we've seen with other pipelines where they work and people start joining and improving them. People need to have a reason to join something and try to work on improving something, but not starting something easy from scratch. Starting something from scratch. Yeah, it is a real problem. I don't think there's like an easy solution to this, because especially with machine learning, people will not necessarily share their ideas because they feel they will lose the paper. There's like this kind of mentalities that I'm not aligned to. But yeah, it is a problem, and I don't have really an easy answer to this as a solution.
But also with machine learning, you have like a huge number of ways that you could do the exact same thing and achieve the exact same results. So which one, just based on politics, if I make one and if I make a pipeline and if someone else makes a completely different architecture and gets the exact same results as me, which one do we take?
So if I can offer just two thoughts on this to you, but one is, I mean, in terms of the organization of things, and organization is important, right? Actually, it does determine the outcome sometimes. I heard a few sort of comments about, the machine learning group and things like this. One thought to have in your head is that we're not trying to build a machine learning pipeline, right? That's not the goal. Yeah. The goal is to find a signal, and there are well-established groups that have that. So my suggestion would be that those are the groups where this stuff should be organized, because they already have the expertise. And I can see Ian very rigorously nodding over here. the other thing to say, and to look at those groups, right? They've already gone through this. They've proliferated their pipelines, and they have very separate pipelines. Maybe there's an opportunity in terms of, and to come back to something Hong said, of infrastructure, right? Like maybe there's an opportunity to have a single piece of infrastructure, right, which does all the stuff, and then you just add your bit, which is your clever bit, right? If that was to happen, I think it would make it a lot easier for people to work on a shared common code base, and then make comparisons easier as well, because you wouldn't have to, you know, fine tune n different pipelines in the same way. So just a thought for people working in that field. I don't know if that's possible or worked. Patrick.
Well, I agree with all of that. I was just going to add a cynical comment, if I can, or maybe a note of realism. I've been asked by senior people in LIGO management, you know, why do you data analysts keep writing new pipelines all the time? And my response is roughly maybe 5% of the time a new pipeline comes up, it's because somebody has had an idea that is genuinely better than what's come before. That's great. Maybe, I don't know, 10% of the time, it's not really any better, but maybe it's faster or it's a bit cheaper to run or has some other nice feature. That's fine. And probably 85% of the time, the real answer is, well, I can write a paper on a new method, right? Or get a grant. I can't really write a paper by just tinkering with an old method. So there's that economics of how science works, that if you need publications and you need funding. And that's actually a real drive to keep inventing new stuff, even if the new stuff isn't actually any more useful than what you've already got.
Microphone somewhere.
I've got the mic because I had it from a while back. So, Matt Pitkin here, by the way, sorry. Just to comment on the continuous wave question earlier. So I think that one thing that would be useful is really if you could restrict the sort of frequency derivative space that you'd need. So if there was a glitch, you can say it will definitely be within a millionth of the rotational frequency. It'll definitely have a sort of spin down of this in this sort of range, because that could really help restrict the feature space that it has to learn on. Or similarly, if it's a known pulsar signal, what sort of the deviations could be from the EM frequency evolution would be useful to know. Again, that could restrict the parameter space. So that's my comment on that. And as I've got the mic, I may as well keep it for a second. Just in terms of to preempt the poll and to bias everyone, talking about interpretability results as we have been, and in particular, knowing exactly what the machine learning algorithm is doing, that could be a sort of infinite effort, very little gain thing. Do other people agree that it could be an infinite effort, very little gain thing to, again, bias the results of the survey?
I think complete interpretability of machine learning is impossible. If you had complete interpretability of something, it wouldn't probably be a machine learning thing. It'll become a classical method.
Okay, so we have Nihar has a hand up, and there's also a question on, the question online has now just disappeared. But I think I remember what it was, but I don't quite remember who asked it. It was, is there work at all on the development of FPGA or use of FPGAs? Is that of use, or I can't remember exactly how the question was phrased, but it's disappeared. So does anyone want to speak to FPGAs? Can anyone give us a quick definition of an FPGA?
Field programmable gate array. Field programmable gate array.
Thank you. I don't see anyone from the panel, but I don't believe that there's anyone working on that within the LVK.
I think there are papers with gravitational wave detection and FPGAs. There are a couple of papers that I've seen, I think, but I'm not an expert on that at all, so no comment.
Okay. There's hands up all over the place. Nihar next, and then we'll go.
I remember it
Nihar first, and then.
It was on the FPGA. Just a piece of information. Back in 2012, I believe there was a group from Korea, I believe, who were working on FPGAs. That didn't. I don't remember if they made things work. There were some problems with efficiency. But yeah, there are probably a couple of papers on this from back then.
Okay, thank you. Nihar?
Okay, I have a question that's not too related to machine learning, but we started talking about FPGAs, so I wanted to ask it. So has there been, so I was reading this paper from Facebook the other day in which they wrote a algorithm to basically find the minimum search distance between like two vectors in like a very fast way using GPUs. So in that sense, you can maybe do something similar for like waveform mismatches, right? Because it works very well for high dimensions. But more in that area, have there been classical methods that people have been tried to put on GPUs? And like, does it work well or does it not work well?
I think so. I mean, I can speak with the CW side of things at least, but quite a few of those have started to use GPUs to more efficiently compute things, right? And that has sped up things quite a lot. So I think there's certainly benefit of doing that. GPUs are really, really useful things to have. And I think it's been used in lots of other areas as well.
Yeah, there's also GPU-based waveform generation stuff, which is super helpful.
Yeah, so Ian, Harry, yeah, we on the search side, one of the low latency pipelines, Spear, is using GPUs off the bat. Unfortunately, due to the fires in Caltech at the moment, the part of the compute system that it's running on is on fire, so that's not running right now. You know, my thoughts to the people out there. We have also run PyCBC and GSDL have both, in terms of the CBC pipelines, both developed GPU algorithms, but it's really hard. GSDL are better at this than we are, but it's really hard to make these efficient because when you go to machine learning, at some level, the core is always the same, right? You're just doing linear algebra and shoving stuff together. And whoever's written that really has understood a GPU and done something then that really is a catch-all for everyone. It's very hard when you're writing custom kernels. I've had to learn CUDA. I mean, I can write it, right? But my efficiency is 2 orders of magnitude less than what the fancy TensorFlow people can write. And for me, that's a problem, right? I don't know. I'd love to have that knowledge of GPU coding to get that 2 orders of magnitude back, but it really holds us back because when you can't just plug into the standard routines. You have to write custom code to do it. This is also true in the Lisa sphere as well, where GPU usage is much more prevalent, both for searches and parameter estimation as well. Again, limited by waveform generation and the translation of the waveforms into the time domain interferometry frame that Lisa uses, normally dominated by that latter part. Again, dominated by custom kernels that people have. Michael Katz has probably got the best that I'm aware of for this. Again, it's dominated by that. And when you profile it, it's using about 1% of the GPU, right? These are horrible. So some real GPU expertise, I think, would really help those methods across the board.
Thanks. Here we have a hand up from Vivian.
Hi, Vivian Raymond, Cardiff University. Just one quick point on this. There has been a huge amount of improvement in our ability to develop code and test new methods, with first moving from LAL in C to Python. And those of you, most of you I'm looking around probably don't remember that, but yeah, Python wasn't always around. But especially for machine learning, the efficiency at which you can try a new idea and test it, and it all works very efficiently on the GPU has, over the past few years, has been incredible. Even people who, such as myself, who don't understand a lot of the technical details and wouldn't be able to put it efficiently on a GPU, it's actually very trivial with a lot of very well-written routines to do that. So there is an argument about not trying too hard unless you're very certain that your new method is such a leap forward. There's an argument against spending too much time coding up very specific gravitational wave algorithms or methods into a very specific hardware, because very quickly the hardware changes and you have to do it again, and the gravitational wave field changes and you have to do it again. There has been some anecdotal evidences in the past of coding things up that by the time they were efficient enough, a new waveform had come in, or the field from a scientific point of view have moved forward. So this is not against having very good understanding of the hardware and being able to use it efficiently, but there is something about, sorry, there is something about putting that effort and coordinating that effort very well so that we only do it in the places where we're reasonably confident it will pay off in the long term. Which goes a little bit into what Patrick was saying. There is this argument, 85% of the time, and I can believe those numbers actually, 85% of the time we write a new data analysis method because we need to write a new data analysis method. The slight, it's not a counter argument, but the slight thing is, as a field, sciences and all of that, the new idea, the potential of the new idea, the one that will break the field, paradigm shift, everything, that one is so great that we really cannot miss it. It's true that maybe only 5% or maybe 1% of the time, it's actually something that is worth it. But 0.1% of the time, that new ideas makes everything 1,000% better. And I'm sure we could do this a lot more efficiently. Don't get me wrong. I'm not trying to defend the status quo, but there is something to be said about being able to try a lot of things. And yeah, most of the time, actually, it's not that impactful. But if you hadn't tried, we wouldn't know. And you need to have some incentive for trying in the first place. So the reason why I'm bringing that up is I think it ties into the argument that there is a lot of benefit from a field to having this common framework, which is not just gravitational wave specific common, but also piggybacks on a lot of the overall machine learning and GPU programming communities framework so that we can go and explore and try new methods quickly and efficiently. We probably want to have some, as a lot of people here have worked on, gravitational wave test beds that is very easy and efficiently for an applied mathematician who just developed a new, neural network architecture to test it, because maybe they can make it work on the egg box problem, but we have real data and things are different. So I want to say there is what we have, we need to do it as best as possible, but also we want to keep the very blue sky exploring aspect of the field. Just
thanks, Vivian.
A rant a bit, sorry.
It's what we want. We want rants from everyone in the room by the end of the day. Right, more questions? Just the one. Matt?
So Matt again. Just again, with the practicalities of using GPUs in particular for sort of the classical things, it also depends how much, obviously how much you can put on the GPU and what sort of throughput speed you need to go to the GPU, because transferring stuff from CPU memory to GPU memory can be a bottleneck in a lot of the time. So if you're actually not doing much on the GPU anyway, it's maybe not worth it. Other things that you can think about potentially are if machine learning specific, if you can quantize your model. If you're working just particularly with power spectra and you can all work in 8s, then you can potentially speed things up a bit. It probably won't matter if you're using your normal computer or GPU, but this is more thinking if you want to put it on an embedded device or something and you've got to be power efficient, but doesn't really matter for this. But it potentially is another aspect of slightly speeding up models if you can work in a quantized integer space.
So I have another question for the panel, and it was inspired by a comment here. So machine learning intrinsically learns from examples, or in the fields that it is widely applied, there is labeled data sets of things available. We're intrinsically in a field where we don't actually know, the things that we've seen, we don't know for certain that they are what we say they are. We only know because the pipelines have told us that. So my question is how, is machine learning the right tool in that field? Is that one of the things that we're sort of edging around here a little bit? Like, do we always need to have, so I think what the comment you made earlier was, maybe it will find a pattern that we weren't expecting. But my question is how would it ever be able to do that if you haven't already told it what the pattern looks like?
Just as a very quick response, it's a good point. Maybe it's not the right method, but it is, I think, obviously intrinsically better than a match filter approach, which is the standard alternative. So we're not doing any worse by moving over.
But
it's a good question.
By that, do you mean that in cases where you simulate, for example, we have models and we can simulate something in it?
Yep.
Okay.
Yep. So you can always add some sort of perturbation to your signal if you're not sure that your match filter models are exactly correct, you could always generate a training population where you deliberately perturb the signals in some non-GR way, right? And train with, so you're training with a slightly wider signal set, presumably give you a more robustness in detecting, signals that are slightly off from your model. But with a match filter, that's really not practical, right? Yeah.
You can also do this sort of the other way around, where with like anomaly detection, right?
Yeah.
Where if you understand your noise really well, you can train it on just that and see if there's something else which isn't noise.
That's also the point with CBC detection, where I've had this question a couple of times before, where what if you have an undetected signal, a signal that's undetected by match filtering in the noise that you're using to train the machine learning model? Then does that matter? Then to that, I think that's related to the question that you asked, and to that, the usual answer is the data that we're using is noise dominated, and it's a huge amount of noise compared to a really small amount of signals. So there's a bias against the volume of noise features you have to the volume of signal features you have. So no, so even in that way, it's pretty robust.
The 99.9999 level that Patrick quoted.
Sorry, do you want to repeat the question? Maybe simpler.
Someone say it.
Yeah, is it still robust? Patrick said you're not aiming, your plot you showed was not the 99.99999% level that Patrick said is needed. Is your statement still true if I take Patrick at his word?
Okay, it should be, because I can't say because I haven't tested it completely, but it should be because let's say I take a year's worth of noise. How many signals is match filtering going to have completely missed there? It's going to be extremely low SNR, and it's going to be low SNR, and yeah. So given the volume of noise features, it definitely is not possible to learn. For example, during the training that I was doing, I provided it signals of sufficient SNR where the signal duration was pretty long. So if you look at a typical, if you take an astrophysical prior, and if you look at the signal duration distribution, the prior for signal duration, what you'll have is it'll be pretty large when it comes to low durations, and then it'll kind of go down, and towards the really long signal durations, you don't have as many. And in that case, I'm providing it signals, long duration signals, which are of pretty high SNR. It still doesn't learn them at all. And even in that case, if it doesn't learn, then in this case, it's still not going to learn at all, I think.
I think specifically for searches of low latency, I think if you make the devil's advocate, machine learning might be avoided for CBC searches if you have always like the best simulations, the best hardware, all everything is organized in GPUs, parallelized. You can make it as fast as possible. Run the P there, everything's ready. Theoretically, you don't need that for CBCs. Assuming you improve all the time. For unmodeled searches, though, you always have the need to do a big background search, and that's really expensive. And the more accurate you're going to be, the more expensive the background search is going to be. What machine learning can help you there is reduce the parameter you actually run for the background. So the calculation is might be much smaller, so you can run backgrounds much faster. And I think that's it can be crucial for unmodeled searches. CBC searches can be avoided, but that's what I believe.
Thank you. Okay, we've got 5 minutes left, so probably time for one more question. Sorry, can you?
Did you want to pull results?
Oh, how long will that take? 5 minutes?
Show the results and kind of if there are any outliers.
I don't think there's a way to show the results.
Oh no, there's a way to show the results there. They can.
Oh, okay. Okay, let's see. Is there any last questions that people have for the panel before we move to the results? No takers? Okay, so yeah, we can move to show the results. Do you want to take us through them?
Yeah, I think they just asked us to tell them that.
Okay.
Move the panel.
They've just disappeared. All right.
Changes.
Maybe you can go for a break and then get back to.
We could do it. Yeah. Yeah, we could do it. Like if we could break now and then come back 5 minutes earlier, saying.
Should the dots on top of each other? Yeah.
Oh, let me guess. They're all pretty much in the center. Oh yeah. Okay.
I'll let you explain that. Okay. There will be.
Okay, I think we're now.
Oh,
there we go. Okay.
Huzzah.
Get away.
Can they cover the most sort of to see individual points? Unfortunately, I can't do that.
So everything is a medium amount of effort and a medium amount of impact. Is that what we've learned?
I kind of
We're all
expected this.
slightly above average.
Yeah, yeah.
as far as it's the-
But I think the individual points may be scattered. Yeah, yeah, could they do that?
Could the chat, could you? what
Could
do
you
wanna
hover
do?
hover the mouse on top of the points? Yeah.
Oh, wow, look at that.
Look at this.
Oh, that's interesting.
So,
Perfect, thank you.
so one, for example, interpretability. Some people think it's super high impact, super high effort. Some people think it's super low impact and super low effort. Why is there? So
Could we get the
Go on,
left
debate.
person to help us? It's obviously that's the-
We're supposed to be able to identify.
it's still anonymous.
I'm pretty clear there.
It's still anonymous. But there's clearly some people who are completely who have completely different views. So why is it? Can someone from either side comment on it if you can?
Who is it who sat in the top right and want to reveal themselves? Vasilis.
Yeah, out of experience, I mean, as Patrick said, if the opposite side, please come join and tell me how you do it, how you will do it with low effort. It's because every time you try to do some interpretation, you realize that the interpretation has a bias based on something else you think about, and it's never that it was never a simple answer. So there are many cases where I've created like new endeavors of new of a new problem because I was trying to interpret what I already have. So it was like it's much more complicated.
Yeah, sorry, it's Lucy. I was also in the top right because I think we talked earlier about how is interpretability of ML results a never-ending problem that will never actually get to the. So I therefore think it will be infinite effort. But if we do somehow miraculously get there, then all of our issues about how can we trust our machine learning results for anything will all disappear. So.
You want a different point, maybe?
Yeah.
Number 2. Yeah.
Could you?
Quickly.
Yeah, maybe. Could you move the mouse to number 2? Thank you.
Similar. And there's one point which say that it's really low impact but high effort. Why do people think it's really low impact?
I think that's not my point, but I was somewhere near there in that. So the reason I said low impact is just because in my experience, machine learning methods, I was thinking impact in terms of efficiency computational. They're already so much more efficient than the standard searches. Doing any further optimization is sort of pointless, roughly speaking. You know, we're already 2 orders of magnitude down or something like that. So fine. So not much impact, but it would be a lot of work. It's always a lot of work to optimize anything.
Okay, I'll put a couple of points against it, which is one, I mentioned biases that can exist, which change during training. So if you want to train something that for a really long time so that it gets rid of those biases as much as possible, then you need something that's efficient so that you can get to that point. And if you have an LSTM, for example, and if you're comparing it to a transformer, then if you're running an LSTM, if you're running a transformer for say a month to do something, then with LSTM that'll be an infeasible amount of time to do something. So,
but may I just counter, like how many GPU hours are you talking about in your mind for this one of these analyses?
I'm not sure. But.
Okay, so a small LVK search is 1 million CPU hours, right? So if it's not 100,000 hours on a machine, I don't care.
Okay,
right? That's nothing.
And another point against that would be, let's take, if there's a coherent search, for example, we have to do time slides in order to get to a really low false alarm rate. And if you have a coherent machine learning search where it's looking at end detectors, and if you want to do time slides, then you're not shifting the triggers, but you're shifting the HFT itself, and then you're re-evaluating the models. So even if you have something that can evaluate a month of data in 30 minutes, and if you want to get to a false alarm rate of 1 a year, then you have to run that model for 30 days. So that's where this efficiency is good. So if you have a model, even though it's much faster than real time and can do a month of data in say an hour or 2 hours, it's still not fast enough in this case, if you're doing a coherent search. And if you go to a coincidence site, then you don't have the same advantages that you have in the coherent site. But, yeah.
Okay, so that is we're now at 40 minutes or so. So we'll end the session there because I want people to have coffee and to have a chat. We will come back at 55. So please go and grab some coffee, continue the discussion, and we'll move to parameter estimation in the next session.
Yes.
Well, it is an open building, like someone could technically walk through, but I'm gonna leave my laptop.
I think if we all leave our stuff, the chances that yours is the one that's stolen is very, very small. Yeah, it is, I am in favor of more efficiency. I was just thinking from the point of view of like LVP management, we have so many computing resources, how much do we spend? And then you get a continuous wave search being 10 million hours to do something. And you're like, okay, my search goes from being 10,000 hours to being 5 minutes. That's great for the user because it turns stuff around. But from the collaboration, we don't care. We didn't even know about the time. Nobody noticed you were using 10,000 hours before. So, yeah. So it's, I guess it's different metrics for different, depending on, where you are sort of in the organization. Definitely faster is always better.
As well, like personal time it takes to get that. It's like, you save an hour, but it takes you a year's worth of that.
Yeah. I do, with the Facilis and my other, my students, they're like, trying to, this code's too, I don't want to run this analysis, it's going to take a whole week on this CPU or GPU to run, like, that's it. To me, it's negative because I'm running the million CPU hour searches as a normal thing. It's like, well, what do you mean it's 168 hours? So can't just do it, right? We have to wait a week, but it's not like you're hogging resources from somebody else, just run. So I've just noticed the students who have started doing machine learning, their scope of what's a big CPU use of GPUs is much smaller than somebody who started with a match filter search because they're used to running millions of hours of stuff and don't think about it in the same way.
I guess a lot of machine learning stuff takes a lot more, if you're in development, it takes a lot of trial and error. And so if it is a week.
Yeah, and you do what, and that's a pain in the ass, yeah. Shall we get coffee?
Yeah.
Sorry, I don't mean to hold you up. You're not here, we don't get at least one raise, and you picked up plural raise.
Yes.
That's right.
It's just.
2 more sessions.
You can do a microphone.
I'm expecting you to very much something.
In a way that you don't have to think about it constantly. Yeah, exactly. Something like that. Yeah, sure. Exactly. Yeah, because otherwise. Yeah. I have it on my computer, but that's all.
The laptop for the question session.
How did Greg did? Did he have his
Yeah,
laptop?
no, he had Matthias.
Okay, I'll, yes.
And they'll just
Same.
pop up there. That's
Yes. If a panel member could have their seat, please. Well, but this looks like a if. Oh, this is you for the project. All right, in the interest of time, I suggest we start with the sparklers, which will also provide the introduction to the panel. So yes, the first slide, sorry.
Not that thing.
Yeah, exactly. That one, that's the one. Sorry, I was looking for, yeah. All right. James? Sorry, should have warned you as sparklers if you could, yeah. You want to grab or actually you can use those mics.
Is that mic working?
Yeah. Yes,
Yeah,
it is.
cool. Good stuff. Oh, and I will try to keep you, on time. I'll do my best. It's not going to be long. Right, hi everyone, I'm James. I'm just started a research fellow at Cambridge. So I'm going to talk very briefly, say a few words about the Lisa data analysis problem and simulation-based inference and how it might help. So first I'm going to start off with a hopefully uncontroversial claim that analyzing Lisa data is quite difficult as a community. There's a challenge there. There'll be no time for follow-up, so I can just say it. But I'm going to call it the everything always all at once problem, which is slightly different to some of the LIGO searches that we've been hearing about. Everything, we have lots of different source classes, things like, supermassive black holes, galactic binaries, MRIs, all of these things together. They tend to be in the data for quite a long time, even some order mission duration sort of signals. And they're all there all at once, so we have to analyze everything at the same time. And what that means is really there's a Lisa data analysis challenge, which is someone has to solve this nominally kind of tens to thousands of hundreds of thousands of dimensions parameter estimation problem. The second claim I'm going to make is that SBI might be able to help. So there are some key features that I wanted to just highlight here of why this might be the case for at least some of the problems in this challenge. So first is you can marginalize, you can turn a kind of 10,000 dimensional problem into a few 10-dimensional problems that you actually want to solve. You can amortize, so you can sometimes at least, you can do the hard work once and you should maybe do it right, and then you can gain a lot. That's actually similar mentality to the search sort of pipeline story. And finally, you can transform. So you can put your data in any sort of format. So I'm going to be close to time already. So if you'd like to hear more about SBI and some of the code that I wrote with my collaborators, this Sakara library, for example, I'd love to chat over coffee. And otherwise, thanks a lot and enjoying the workshop so far.
So nested sampling is a tool that's popularly used in parameter estimation. It's reliable and it's accompanied by an informative error bar, but for typical GW problems, it can be computationally intensive. The runtime of nested sampling depends on a few different things. It depends on the likelihood evaluation time, on how efficiently you can sample new live points, and on how small a fraction of our prior the posterior occupies. There have been several attempts to accelerate nested sampling using machine learning with these first two factors. So that includes accelerating waveform evaluation and by making general improvements to the sampler, as in NESSIE, for example. But this third factor, the amount of compression from prior to posterior, which I think is less considered in the literature, can also benefit from being accelerated with machine learning. Specifically, we can do this with a specialized form of conditional normalizing flows called beta flows, which are designed to better learn deep tail behavior than traditional normalizing flows. And doing this can give order of magnitude speedups on realistic data. So I do have a poster here today. So if you're interested in hearing any more about this, do come and chat to me in the coffee breaks.
Hi everyone, you might notice there's a bit of a theme here. So my name is David, I'm also from Cambridge, so we have a bit of a presence here. Green button, yes, sorry, I've got too many. Yeah. Okay, cool. So I guess it's just a very brief slide, a very brief introduction. One of the questions that I think was brought up in the last session is when we talk about machine learning, typically everyone's talking about neural networks, and you can also view hardware acceleration of classical methods, of which things like nested sampling and other MCMC codes would sort of fall under that umbrella. And the question is, how do we put all of that stuff on a way that optimally uses the obvious benefits of hardware acceleration? There's just a little plot here, and this is a really cool worked example actually of why vectorization is really the important part of all of this. It's not so much to do with gradients, it's really about vectorization. And the broad question is, how can we best utilize GPUs for inference, particularly in these kind of gravitational wave problems? And there's a few different threads in here: SBI, variational inference, and MCMC, where the challenge really is getting vectorized sampling. And I will just leave with a very quick view on something I've been working on recently, which is a nested sampling code that's in JAX, so it's fully vectorized and it's quite fast. And it's not perfect yet. This is a little bit preliminary. I did this on Tuesday, but there's some runtime stats and things like that. So hopefully that's an interesting prompt for discussion. Thank you. Okay.
Right. Lucy for the.
Hello, I'm Lucy. I'm going to give a really brief introduction to start off the discussion. I realized when I was making these slides that there are 1,000 things I could talk about. This is a very broad area. So I'm sorry if I've missed something. Panelists and everyone else, please feel free to bring it up in the questions later. Okay, in traditional parameter estimation, this is what we're looking at. We're trying to get a posterior probability of binary parameters on the left in that sort of purplish box. We have prior probabilities that we have defined somehow. And we have a likelihood function that normally assumes Gaussian and stationary noise and some evidence. And our likelihood looks like something like this on the bottom. And I'm kind of going to look at 3 different things, sort of main topics as we go through this. The first one is looking at likelihood-free inference. So how do we do this actually without evaluating a likelihood at all? Then I'm going to look at how do we accelerate the likelihood by looking at accelerating the actual waveform model itself. And then lastly, I'm going to talk about hierarchical inference. So some terminology first, just so we're all on the same page as to what I mean when I say these things. Simulation-based inference is sort of a broad framework focusing on inferring the posteriors where the likelihood is intractable or difficult to actually evaluate. But simulation of data given from a model is possible. Neural posterior estimation is sort of a bit finer and narrower. This is where we're approximating a posterior given some observed data using neural networks of some kind. Likelihood-free inference is a class of methods where the likelihood function is difficult or impossible to compute directly. So I would say that SPI and NPE are likelihood-free inference methods. Normalizing flows are methods for constructing complex distribution, transforming a probability density through some invertible mappings. Importance sampling is something that might crop up a lot in some of these likelihood-free methods. It allows you to approximate the expected value of a function under a target distribution by sampling from a different one by reweighting of some kind. And flow matching is defining some trajectories of sample distributions during training using ODEs, which you can then solve to achieve your target distribution. So with that out of the way, let's talk about neural posterior estimation. So this is sort of thinking about the likelihood-free part, the first main theme. So rather than attempting to actually compute a posterior directly by sampling the likelihood, we can train some normalizing flows, which represent a mapping from some sample space onto a much simpler space. So that's this function f. And then our approximation to the posterior is given by this transformation. Oh, do I have a laser? Yes, is given by this transformation in the first equation. So where Q is our approximation to the posterior that we're trying to train, and pi is the simpler distribution that we know how to sample very efficiently. And then the KL divergence we use as a training loss function. So on a mini batch of samples, this simplifies to this. So you're only looking at your approximation to the posterior distribution is Q. And so we actually train this by first drawing samples from the prior, then simulating the data, and then we can take the gradient of the loss function with respect to the neural network parameters and optimize it in the same way that we would train a neural network normally. So there's a ton of examples of where likelihood-free inference has been used for gravitational wave parameter estimation here. I'm not going to go through them all in detail, but just to sort of point out the kinds of things that have been done. So using normalizing flows is a really big theme here to predict posteriors. There's also been examples of using neural networks and waveform interpolation together in conjunction with nested sampling, so NESSIE and the importance sampling with NESSIE. There's DINGO and DINGO with importance sampling. And there's also examples of using flow matching on some intermediate mass black hole signals. Again, apologies if I've missed your paper or your favorite paper here. Inevitably, there are some that I've missed. So several of these approaches actually show very promising results, comparable posteriors to the stochastic sampling methods that we're used to with traditional PE in sort of a fraction of the time, minutes, seconds compared to days, weeks. The things that we should consider and that I think we should discuss are the ability to handle a variety of noise realizations, things like non-stationary, and also out of distribution detections. So if we're trying to do PE on something that our likelihood-free inference was not trained on. Okay, so the second thing, I want to look at waveform acceleration. So that's accelerating this h of lambda part. So we can alternatively speed up the likelihood by just accelerating the waveform model, often by using a PCA or a reduced order modeling where the steps are there. You select your parameter space region that you want to build an accelerated model over. You decompose the waveform into things that are smoothly varying and easy to fit, like mode amplitudes, phases. You use some greedy algorithm, you build a basis, you downsample the time and or frequency nodes, and then you do a fitting procedure that would probably, in this context, use machine learning of some kind. And these models can be significantly faster than traditional ones, like over 3 orders of magnitude, especially if you're leveraging GPU capabilities. But the thing that I think is worth discussing is that these accelerations sorry, are most suitable for batch evaluations of waveform models, and that's not typically something that we're used to when we're doing PE in large batches. Also, things to consider that I actually left off this slide are the amount of training data required to build these, and do we have that amount of model training data available, specifically numerical relativity? Also, the training time, and are we sure that we're optimizing the training to get the best and most accurate model? So again, a bunch of examples. GPR surrogates, reduced order modeling for in-spiral and in-spiral merger ring-down waveforms, regression to build surrogate models of EOB and numerical relativity, and also a cool one at the bottom, using neural networks to using neural networks to incorporate the numerical relativity calibration uncertainty. So thinking about the uncertainty of our waveform model fits is something I think worth considering. Okay, and the final thing I'm going to talk about before we move on to discussion is that I've been implicitly kind of thinking about parameter estimation as single event parameter estimation up till now, but also we can take many of the same ideas to think about hierarchical inference. So, for example, the 3 papers there use clustering, like Gaussian mixture models, to infer subpopulations. You can also use hierarchical inference and deep learning, or autoregressive processes to model the population distributions of binary black holes. So that's all I'm going to say. Thank you.
Perfect. Thank you very much. As a way of introductions, this is your panel for the next hour. And we will get through each of your slides. I think that would be most efficient. Just go ahead. Feel free to stand up if that's a little more.
Yeah,
I think it's, yeah.
thanks. And thanks, Lucy, for the intro. That's really nice. So I'm Matt. I'm a postdoc at MIT. And I mostly work on population analyses rather than single source analyses or searches. So when I think of parameter estimation, I'm going to interpret this more broadly as Bayesian parameter estimation, which means trying to measure something that we want to measure, but that we can't measure directly. And so a lot of the work that we've talked about so far is focused on single source analyses, so searches and parameter estimation. What are the properties, the black hole masses and spins, for example, of individual sources? So one question I have broadly is, what's the best approach to combine the data that we observe and using ML methods to make direct astrophysical interpretations from data? So if you use a PE algorithm that's based on machine learning to measure, okay, this is the posterior distribution of the mass of this individual source. Well, what do we learn from that? We've already got 100 black holes. Unless it's particularly massive or particularly light, it's not very interesting by itself. And in fact, the vast majority of things that we see are vanilla sources that don't really tell us much by themselves. So how can we use machine learning to more directly interpret the whole distribution of sources that we see in an astrophysical context? And one way you might do this is to interface these nice machine learning based rapid PE algorithms with downstream analyses such as population inference, tests of GR, cosmological analyses, for example. Another very important thing in this hierarchical inference context is robust uncertainty quantification. So we have a lot of theoretical uncertainties about how we even form the population of sources that we see with LIGO and Virgo. So if you're building a machine learning based model that you want to use to do astrophysical inference on the population, you need to make sure you can well characterize the uncertainty in that model across the relevant parameter space. And the final thing I'd like to think about, which maybe goes into more of the next session, is, how do you envisage parameter estimation and population inference for future detectors? My sort of preliminary thinking about this is that it's going to look completely different from the way we do things now. When you're getting hundreds of thousands of sources, there's no way that you are going to care about PE results for individual sources anymore, unless they're really exceptional. So how will machine learning help us in that future context? So those are the points that I'd like to think about and discuss with everyone. Thanks.
Cool. Hi, I'm Nihar. I'm from the Max Planck Institute for Gravitational Physics, and I work on a machine learning code for about the last 3 years called Dingo. And I basically have 4 points here that I would like to talk about. The first is what actually needs to happen for people who are not interested in machine learning to actually trust gravitational wave results from machine learning methods. Do we need more visibility of the results? And in that direction, we've sort of been analyzing the O4A and O4B events with chirp masses greater than 15 solar masses, and we've sort of created this website. Do we need to show these results off a bit more, or what do we need? Is it more that seeing the results is not so useful, more as like actually getting hands-on experience on running the inference codes? Is that actually more important? And if that's the case, do we need more tutorials? Do we need more workshops? That sort of thing. The second point is what can be done by machine learning algorithms that non-machine learning algorithms can't do. One point that I think gets kind of put under the rug a bit is the fact that an SV algorithm runs on a global sampling scheme. So in that sense, it actually is quite different from an MCMC algorithm, and in some sense orthogonal. So you can maybe combine those two methods. Another one is, of course, kind of, as Matt was saying, large-scale injection campaigns. So in particular, I've been finding it very useful to do maybe 1,000 or 2,000 PE runs. And that's quite useful for like projection studies. So if you're trying to look for O4 and O5 data. And then another thing is, I'm going to say something somewhat controversial, which is that I think actually machine learning is actually better for out of distribution data because you may have a biased result with an MCMC method, whereas in the machine learning case, you have a very extremely bad result. And I think there's not enough work in machine learning so far to actually address that problem. I think one thing that you can do, for example, is to train an embedding network, which kind of does this. It's very similar to what we've been doing with the flows, but actually learn the distribution of the embeddings. And then once you get new data, try and quantify at what significance threshold that embedding is compared to your distribution of embeddings. And so I think there needs to be way more work in that direction for machine learning. The third thing is a question that I get asked quite a lot, which is, can we create a centralized metric/injection set to evaluate the efficiency of different PE algorithms? So there's many different machine learning algorithms, and if we can create like a sort of NMIST or a CFAR equivalent for gravitational waves, that would be quite nice because then you can benchmark across the same data. And the last point, which I think is the most important point in my opinion, how can we incentivize experts from machine learning to stay involved in gravitational wave research? In particular, I think most of us here are coming from the gravitational wave background, and we're very aware of the state of the art in that field. However, in my experience, a lot of the best work comes when you have experts in machine learning who are very aware of the state of the art in machine learning research, working with experts in gravitational waves who are aware of the SOTA in gravitational wave research. And how do we make sure that these people stay in gravitational waves? Because I mean, Google and Tsinghua and all these places are really gonna take these talents. So yeah, that's my last point. Okay, that's it.
Thank you.
So hi, I'm Jess. I'm a PhD student at the University of Glasgow. I have a couple of sort of generic points at the start, and then a couple which have sort of stemmed more from my work and sort of my understanding of machine learning in the field just now. My first point is that how well do we rely on non-machine learning methods to justify the machine learning based results? And is that we specifically rely on non-machine learning sort of based results, or ways to communicate our results, or do we need to communicate our machine learning results better and explain our figures of merit that we use better to those who don't use machine learning tools? My second point is does the infrastructure, and by infrastructure I mostly mean person power, exist for machine learning pipeline maintenance moving forward? Kind of similar to what Nihar just said. How can we encourage people to take up or maintain machine learning pipelines and moving forward, and sort of ensure that we have that for like the next 10 plus years? And especially if we want to use machine learning pipelines or tools more broadly in the gravitational wave field, in the detector science or the instrumentation side, do we have the scope to maintain that as well, when the sort of number of data analysts there is completely different to what we have in the data analysis side? Most of my work currently is sort of after the initial parameter estimation stage. I work on neutron star equation of state inference with machine learning mostly. So these 2 points kind of stem from that work. And my first one is, how do we ensure that we are understanding how machine learning models actually map our physically informed data? And how can we, what do we do with the data space that we have mapped by a machine learning model if it passed specific tests, maybe pass some machine learning based tests, and maybe doesn't pass some non-machine learning based tests, or vice versa? How do we push that forward, and how do we communicate exactly how our machine learning model has understood that space? And is it just a blanket representation like we sometimes think of a machine learning model modeling our space? Is it actually that? And if it isn't, then what is it? And then my final point is building machine learning pipelines based on physically informed or modeled data with specific parameters which are defined by the underlying astrophysics or are understood very broadly within the astrophysical community or electromagnetic community specifically maybe, versus a model agnostic approach where we have a data set and we can just wrap it in at the most simple way possible. How do we communicate what we recover and what is actually useful to the wider community? Is it better if we provide a result which exists in our space and we explain what that means? Or is it better if we start to build models which are based on existing well understood parameters? So that's.
Thank you very much. All right, I think unfortunately Sama couldn't make it. She is sick. I will leave those on just for a few minutes, maybe for the truth. Sama is my student, so I probably know a little bit of this, but I wouldn't want to take over, although she did talk to me about what she wanted to do. So yes, just mostly working, and the discussions here is as has been mentioned before, SBI's capabilities of marginalizing fairly naturally over parameters and models and a lot of other things is something that is not entirely different from classical methods, but is generalized in a way that could be particularly useful and different, and this is something that could form a part of the discussions. And it's not just about waveform systematics, but it's pretty much anything that you can simulate, and that you have some errors. If you can simulate it, then you can infer it. Is kind of the idea. And so, what is the best way to extend that power of SBI to all of the many sources of systematics that we are concerned about, some of which we have some model to characterize, some of them we just worry, and that will only get worse as the number of detections and the SNR of those detections increases. And again, I don't want to take from Sama's work, so I feel a little bit uncomfortable going through in that much details, but if you have any questions on those, please send her an email, and as soon as she's better, I'll try to get her to a conference that you'll be able to meet her in person. She's fantastic, so you should.
Hello. So I wrote some things. I wrote, how do we trust and interpret our ML-based results on data outside the training region? So this is something that's been mentioned a lot this morning. For example, special events with previously unobserved physics. There was a discussion this morning about if you find something on an ML-based search, can you do any sort of, do you have any information from the PE? If you then used ML-based PE, is there, how do we expect those results to look? As Nihal said, maybe they're just bad. Maybe that's the information we have. How important is reproducibility, and is this something we can feasibly expect for ML-based methods? So machine learning algorithms are often thought of as big black box things. So if you train something in a slightly different way, how different do you expect your results to be? And is this something we can quantify, possibly marginalize over? Is this something we should be worried about? And if machine learning based methods are more efficient, what, if any, assumptions that we currently make in order to make our PE feasible, do we not have to do anymore? This is maybe particularly pertinent for hierarchical inferences. So are there any sort of assumptions we're making about hierarchical likelihoods? Can we just infer all of these things together because we now have the computational efficiency to do so? And also, I've realized I've phrased this question the wrong way around, because Nihal said, what can ML do that traditional methods can't? I actually meant it the other way around, that what do we have to just accept that machine learning based PE won't be able to do, and what do we need to do in order to make sure that our traditional methods can sort of cover anything that might be missed? Therefore, could machine learning eventually replace current methods, or how do we see them working in tandem in the future for parameter estimation?
Right, thank you very much. I think this was it. So expect there is a lot questions. Please feel free to raise your hands and we'll throw a microphone in your direction. Or carry a microphone. Can you turn the microphones on? Oh, yes.
Hello.
Oh,
Does
there
that
you
work?
go.
Okay,
Good.
great. Thank you.
Sorry.
Yeah, Patrick Sutton, Cardiff. So I guess I was actually a bit surprised. I think all of the panelists put how do we gain trust in machine learning methods as an issue. And I kind of expected that on the detection panel that I was on, because, you know, we're doing this 1 in a billion sort of false alarm probability type. And are you really sure the algorithm works at that level, especially if you have an unmodeled burst or something you've never seen before? I would have expected for parameter estimation type problems that you would inherently have more trust, because I think you know what you're doing better than we do, don't you? Okay, I'm not really forming a proper question, but let me just ask this as a question. If, I think maybe it was Lucy, one of you said if you had something that was outside of the standard parameter space, would you trust the results from machine learning? I would counter, as a non-parameter estimation person, not an expert in that, I wouldn't trust standard methods for an event that was outside of the parameter space that we had experience working with. Because when I've watched this happen occasionally in the past, it seems that if you take one of the standard methods and you have to extend your parameter space, I mean, you're shifting the priors, and these MCMC methods can sometimes give, it seems, my impression is it can give you results you did not expect when you change this, you know, the setup of how it's run. So I'm not sure if machine learning is inherently less trustworthy than our standard methods if you're going sort of outside the tried and tested parameter space. So I'll just invite people to comment on that.
Yeah, I think this is relevant for all of you. So maybe Nihar, because you had that very specific point, and then Lucy.
Oh, this works nice. No, I agree. I do think I would not. I mean, if your model doesn't include something, MCMC is going to find the mode which it finds, which may not be the best mode if your model doesn't include it, right? What I meant more was from a political point of view, which is that how do you get people who are not so aware of machine learning to begin to trust the results, and what metrics do we need to, communicate? The thing that I also think in terms of out-of-distribution testing is that right now we do the importance sampling, right, which can flag out of distribution data. But I think there's also other things that you can do. So to expand on that point that I was mentioning earlier, for example, what you can do is take the machine learning algorithm that you've trained, throw away the flow component, and then just have the embeddings. So now you have maybe something which takes in gravitational wave data and then gives you an embedding, like some vector. Then you create a distribution of these embeddings across your entire parameter space. And so once you get new data from, like, I don't know, cosmic string, whatever, and you find, okay, where in the embedding space does this lie? If it's like 10 sigma out from what your model detected, then you know it's out of distribution, and you also know in what dimension it's out of distribution. So, but I think there's also like, I don't know, 4 or 5 other ways that you can accomplish that, which gives you more ideas. Yeah.
Is this a comment on the same topic or is it different?
A similar topic, but I'm happy to
Just if someone else in the panel also wants to speak up to that point.
Yeah, I mean, so I was thinking about this as that maybe what I was more thinking about is that if you get parameter estimation results with traditional methods that don't make sense, it's very easy, and we have lots of cases where for events where you can just run more traditional PE runs, changing settings slightly, and then you get a whole suite of sort of diagnostic runs that are in some sense a bit independent because you've changed things and you're sort of investigating. But aside from the cool thing that Nihar just mentioned, because of the global sampling nature of a lot of likelihood-free inference, I think it's more difficult to do those kinds of things and to get these sort of diagnostic, really investigatory detective type things going on. That if something is happening with your parameter estimation results, perhaps it means that you have to retrain a whole new SBI model, and that's significantly more expensive and difficult. But yeah.
Before moving to Greg, sorry, just to clarify and help the discussions, I think we need to separate 2 different things. There is trusting Bayes' theorem. I have this model and I have this understanding of the data, and I can write Bayes' theorem. And if I had the magical black box that gives me exactly that posterior, is that the right posterior? Do I trust it? And there is my magical black box actually getting me that posterior or not, which are slightly 2 different things, which both machine learning and traditional methods can fail in different ways. So I think this is slightly 2 different discussions, and I just wanted to highlight that, right? Like, do we trust the model as opposed to, did I actually get the posterior?
So I'm going to talk on the sort of trusting of ML approaches, and also suggest you mentioned the metrics, right? And this also came up in the first session, right? There's metrics within machine learning. I realize that they're there, and I realize that they're useful, but I think that we have a community that has, decades of experience, and there is already a lot of good metrics out there that we use to judge our approaches. And I think that using those is the right thing to do for 2 reasons. One is that they have been thought about in the abstract. So, it's not like we only have one approach that's sort of the standard approach. There were multiple ones developed sort of early on. And we know why some of them don't work, and those metrics tell us why. So I think that it's, useful to look at them. Now, I do understand that some of those metrics, you can't use the machine, it doesn't fit in the context of it, right? And in that case, okay, then we have to think differently, and maybe there are new metrics that could be developed. But that brings me on to the second point, which is that metrics are one thing, right? Putting up a plot and, saying, hey, if it's above this, it's working is great. But actually, I think there's an element of community knowledge that just has to be learned. And some context on this. So when the transition from sort of LAL inference to Bilby, there was a lot of mistrust of Bilby, and rightly so, because early versions of it were sort of inherently broken. But it took time for people to gain familiarity with the kind of outputs, like even just the thing that came out of the terminal was different, and people had to gain familiarity and understand what that meant. And one thing, and this is not an accusation that anyone is not doing this, but just some perspective, one thing that really helped was being very open when things went wrong and doing very public examinations of the problems, showing, how we fixed them, and then saying, look, this is what was going wrong. Now we've solved it, and now we know how to do it right. I think that built a lot of trust in the process. Because ultimately, whenever we take posteriors, there's no way I can go and check everything that everyone's ever done. I have to effectively have trust in the people that wrote the software and in the people that are using that software. And so I think there's a huge amount of sort of person trust, if you like, that needs to be developed. And I think that everyone is going in the right direction. So keep it up, I guess, is what I would say.
Yeah, I'd say I do agree. And I think alongside the metrics that we know and love and we know and trust, a set of machine learning metrics that machine learning, engineers use in developing a tool should probably be brought alongside that and should be well communicated. And if there's an understanding of, in the machine learning community, we use these set of tools, and this is exactly what they mean, and this is why they're worthwhile. When we move forward and we have tools which are doing sets of analyses which traditional methods then can't replicate on the same sort of like either time scale or computational scale, then we have the base understanding now that we're all mutually agreed that these machine learning like figures of merit are useful, but also like we don't need a machine learning engineer in the room to like talk us through everything. And I think that's what I'm trying to say with communication, is that maybe we're just sort of like rushing to the finish line a bit too quickly and sort of going like, yeah, we all get it now, like a neural network does this and then we do a loss curve, blah, 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 full stop. But like there's like steps before that and the sort of level of mutual understanding needed, I think.
Any other, oh, yes, of course.
So just regarding metrics for these things, metrics that provide meaningful information and have error bars. So I'm working in the audio domain now, and in audio, you have all these papers of speech enhancement algorithms that say, I'm best at PESC and STOI with no error bar. They just go on, well, out of all these other ones, I'm going to bold mine in this table because it's the best for this particular case with no error bars. You have no, so it's just a warning to say that it's useful if metrics have some sort of error bar, so they're a bit more meaningful and interpretable to the to people that are looking at them.
I guess just then, chair's prerogative, unless I see a hands up or in the chat, but to echo both what Greg and Ian said earlier, this is not a machine learning problem. This is a brand new techniques problem. The same problem was there for classical techniques 20 years before the first detections, when Bilby came in and showed that actually now modern off-the-shelf samplers are able to solve the parameter estimation problem, which they weren't at the start. So things evolve, and yes, you have to go through, but a lot of the techniques and understanding on how to check whether things work have had to be developed. I mean, as Jim said, even classical techniques that have been developed for 20 years are not trusted by everybody in the field. Neither should they. I mean, the skepticism in this case is healthy. There is no other, at least for now, gravitational wave detection collaborations that will call you up if you say it wrong. The buck stops here. So yes, we ought to be very skeptics. And in terms of machine learning, there is all of those things. I guess my point is, I would try to not invent new metrics and new techniques to prove, but instead try to meet the ones that other pipelines had to. And, all of the internal machine learning's diagnostics that are very well known in the machine learning world are incredibly useful to develop. They're not that useful in the gravitational wave context. I mean, your training loss can be fantastic, but still don't know what you're doing. Like maybe your Tucky window parameter was wrong. And so it's just, all of us here, I think are pretty familiar, but it's just more of an echo of, this is not a machine learning specific problem. Skepticism to new techniques is and will always and should always be there for any new techniques. And I guess I'm looking at Ian because skepticism of all techniques should still remain there. Sorry,
I have another question, Greg. Do you want to ask something related to that? Okay, I'm Vanessa Graber. I have a question for all the panelists. So what is the main challenge during your weekly work that you encounter when you develop your PE methods using machine learning?
I have a very pragmatic answer, which is that GPU availability. So just computational resources can sometimes be an issue. You really want to train your models on GPU, and sometimes you might want to train many models to compare the results. And sometimes you just don't have the hardware resources to do that efficiently.
On a week-to-week basis, it's a cluster issue. No, I mean, yeah, on a week-to-week basis is a bit harder, I guess, to say. But I would say like engineering problems, like for example, making sure that your data throughput is fast as your GPU evaluations, like things like that. Making sure that your data loader is loading data fast enough for your GPU to process it, or that you're not doing too much context switching between threads or something like that. That's the day-to-day issues, I guess.
I think probably making sense of results, and with a limited batch of training data available, I think making sure that the result I have is reasonable when I don't really know what I should expect it to look like. And also just trying to communicate that to other people and validate that. That's probably week to week, yeah.
Kind of on the flip side of having a limited batch of training data, I don't know how to store my training data, because if you're able to generate your own training data, you need lots of it. And so actually being able to store it and process it in a way that is good, like, you know, you have enough memory to do and enough storage space, I find annoyingly difficult.
This is a question for all panelists again. Regarding reproducibility, it happened to me many times that I'll make an algorithm, I'll run a training, and then for some reason, I'll have to run it again. Exactly the same training, maybe with different initializations. And the results might be different to the point where when I come to compare improvements, like I'll change or put an extra layer there, the variance that depends on the initialization of the model or the data, the way the data was trained, can affect significantly if the claim that this method is better than the other. Where in analytical methods, you only have one method, you don't have to try it. And I've used an approach where it's like retraining the same model with different initializations, taking an average and claiming that the average of this method is better than the average of other method. Have you ever encountered something similar and you, when you say, oh, I didn't improve and I need to claim that this is better than the other?
So I haven't personally, because actually no one's ever done exactly the same thing as I have. Or maybe that's a bad thing. But I guess there are sort of two ways to think about this, that if you've got two competing machine learning based methods, do we make sure that both of them are completely optimized and are the best that they can be? Or do we make sure that we include an uncertainty over variation in fit methods, for example, or in how we've, you know, initialized the data? Or is it better that we get the best possible method, or is it better that we include the error that we think we expect when we are talking about which is the best? I don't know the answer to that.
Yeah, maybe to follow up, I think there's a question about uncertainty quantification more broadly, which is something that Greg mentioned earlier, is that there's always something on the right-hand side of your conditional bar. And when you're training, for example, a normalizing flow to do parameter estimation, you're conditioning on all of the settings that you used for training, the architecture, and the final weights and biases of the trained model. Now, in principle, you can be Bayesian about your machine learning model as well. There's a whole bunch of work in the Bayesian deep learning literature, but in general, it's a much more difficult problem characterizing the uncertainty in your model itself, because you're dealing with this abstract high dimensional space of the model structure itself. But I think that's maybe a road we should be sort of walking down and pursuing, is can we more robustly check that, you know, even though our model predicts a distribution of values because we're doing parameter estimation uncertainty, parameter estimation, there should be some additional uncertainty that's folded in through the uncertainty in the model, the training procedure, and so on.
Greg, you had a...
I have a question about the methods. So following the literature on SBI in particular, I know that there's other things that are going on as well. But in SBI, there is a sort of constantly, I mean, it's literally 4 or 5 years old as a field. Each year there's a new algorithm, and as a non-expert in it, I think that the details of the algorithms are rather difficult to understand. But something that sort of strikes me, and I would be curious to hear what you think, is, are we at the point where the latest and greatest thing is going to be stable for a year, 2 years, 10 years? Because if it's not even a year, is it even worth, like, let's say I have a person, I'm going to ask them to spend a year implementing method X. If it takes them a year to implement it and method, X+1 comes along in a year's time, then everything that they've done is just worthless. So how do you think about that? And I guess, how do we solve that? And when will we reach stability of methods?
Yeah, that's a great question. I guess the one thing is, like, the only time to create new methods, in my opinion, is when there's a need for them, right? So in the case of Dingo, I can say there was a need to create, multi-manning heterodyning and the frequency masking for binary neutron stars. And I think in the area of, like, at least LIGO stuff, that the needs right now are the mass range of 15 to 2 trip mass, and then also real noise, and then also adjusting to anytime you change the Tukey window or you increase the Salzer prior. Like, those are, like, I think the 3 things which there are needs for. In terms of, will there be like a thing in 1 year that completely changes stuff around? I think that depends on if there's a breakthrough, and you can never really predict breakthroughs. Did I answer the question? No, not fully. What was the question again? Sorry.
I think you did roughly answer it, which is it sounds like there's a great deal of uncertainty, and it's entirely feasible that next year there's a new SBI approach that kind of blows everything else out the water, and we might have to sort of start again.
I will say that, like, at least within Dingo, we tried like many things, and many things didn't work. And then we iterated on them until they started working. But the timeline for that, like, I don't know, like the PNS stuff was in development for like 3 years before it finally started working. The next big thing, I don't know, maybe 5 years. But I think it also depends on breakthroughs in machine learning, more than breakthroughs in gravitational waves.
I think that's what I was referring to. So, for example, the SBI package, right, has all of these sub packages within it, and each one is a different implementation. I guess my point is that it seems like that field is still in the early stages, and I don't think, it's worthwhile maybe looking back at like nested sampling, and if you go back in Lal Sweet's history and look at the different implementations of MCMC and things, it is very similar, right? There's the broad idea, but there's the specifics of the implementation, which can give you orders of magnitude improvement. And as people learn more about that, eventually you find something stable, right? Like the kind of nested sampling and MCMC algorithms people use nowadays are broadly the same over the last decade. I don't know if we're in that case yet.
That's a good, I mean, my intuition is no, but I do think one thing which will stay constant is we'll have like some kind of embedding and some kind of density estimator. And I think people over the next 3 years are going to try different embeddings and different flow density estimators to see what works, I guess. My intuition is no, but I don't know, I could be wrong.
I think one thing that maybe might change is that a lot of these models and methods weren't originally developed for scientific inference. They were developed from the machine learning literature to generate images, for example. They wanted generative models, and that's how normalizing flows came about. And sort of the target use case that we have is very different to the original reason these models were developed. So maybe in the future, now that the sort of scientific inference point of view has become more well developed, people from sort of our side of those research areas will be driving development of the models because we have specific use cases.
All right, 2 more questions over there first, and then
Hi, James Alvey at Cambridge now. It's just a follow-up on this discussion, actually. Greg said a few things I was going to say, but I think I was going to make a slightly, simpler point, which is, I think something to bear in mind about these SBI methods is that they do solve the same problem, right? They're all doing Bayesian inference. The point you made was the one that I was going to make, like nested sampling, MCMC. One of the reasons why maybe we're perhaps not too concerned about a slight proliferation of those is that we know that we're ultimately asking comparable questions. The other point, which I think is also related to things like the SBI library, is the threshold for trying out these things is becoming lower and lower. And I think something that Nihal kind of alluded to is that they all have their own relative benefits and strengths, which can be slightly subtle. And actually, we're still learning about these methods, and we don't know actually, hey, that scales really well, or that has very good performance on that problem. At the moment, it seems like we have to try that. So yes, maybe the stable state is not there, but saying that it's not worth trying because there's lots of methods feels a bit premature to me. That's just my point of view. I think we don't quite have the same understanding about the sort of scalability, portability, usability of these methods to draw that line. Of course, that costs time. So we do have to be careful, but that's just some commentary on that. But yeah, cool.
I also wanted to follow up on this. So I don't come from the gravitational wave parameter estimation side, but I am interested in Newton star properties. So I will talk about, I guess, a little bit later in the session. But the methodology in this field hasn't really been used at all because we don't really have the ability to use the classical sampling method. So we really have to kind of rely on these SBI methods. And I suspect from reading about the literature on the gravitational wave side, how this is implemented there doesn't really work for us. So there is definitely differences in how we use these methods and how we want to push this. But I suspect in the future, in the next generation of gravitational wave signals, we will have to do a lot more of what people in other fields do, just because what we've done so far will not work because the signals will look different and we can do different physics with it. So, I think we really have to be open to the development of these new methods and also be curious about what's out there, because we might just not know what will be useful in 5 years down the line. So I think it's really not really, you said waste someone's year of implementing a new method. I wouldn't really see it. In some sense, you have to really dedicate some time and work on this. And I think we as a community, I think on the Astra side, it's really a lot more difficult to convince people that method development is worthwhile and is a really is part of the scientific method, because I very often see this in referee reports and so on, that method development isn't science, and that's really disappointing in some sense, because there's this thinking that this isn't really part of the whole process, but it should really be part of it. So I think that we should be happy to dedicate some time in actually developing these methods and then actually applying them to some of the science cases that we have, but also make sure that that's some of the things that you said earlier about losing all this talent, because obviously people do go. There is lots of other job opportunities. So that we kind of also make this part of the scientific community and say, okay, look, this is important. We appreciate you can go somewhere else, but we do actually value this in this field as well. So if someone does spend a year implementing a new method, I think this should be valued as a community, that someone takes the time and actually does this.
I really agree with that. And I think it has to start from the top down. So, the senior people in this room, when you're hiring postdocs and PhDs, you have to make sure that you tell them that you value method development and not just the sexy new astrophysical result that maybe will be irrelevant a year down the line because there's new data, but it got 100 citations and that's what's valued in a job application or a fellowship application.
Sorry, I know you have the mics, but this is, I think, a direct response to this, unless yours is also a direct response to this.
I'm interested to hear what you said about method development. I think, at least for the early career researchers in the room, I would point out that the UK in gravitational wave astronomy is probably the best country in the world. I'm going to put myself out on a limb there, but for delivering new methods in gravitational wave astronomy, right? The search pipeline, the parameter estimation toolkits, the detector characterization methods, some of the instrumentation as well that went into the detection were all developed in the UK. I'm concerned, if this isn't valued in other fields, but I do think that at least in the UK, we do have a good history of valuing that. And the people then who are reviewing, your URFs and your ERFs and things like that are people who have come from that as well. And I think we do have a good history in valuing and appreciating that. And of course, you know, the person writing that has to understand that these lead to scientific payoffs, right? And they're not just doing it because it's fun. But I would sort of try and reassure people a little bit that I think these things are valued in GW. I don't know what, you know, other you called out senior, someone called out senior people, I guess. Perhaps I'd ask if others agree with that, but.
So I would agree. Is another gray hair, proper gray hair. Yeah, so I would agree with you on that.
I can also make like a somewhat tangential point to that. So my point on the losing talent was like in that direction, but also is a little also subtle in that I think that people that work in like machine learning and computer science are actually not always necessarily that interested in gravitational waves. So the point that I was making was that we should let them kind of focus on the aspects that they're interested in, and then let us focus on the aspects, you know, that we actually care about. So if that means that they're not necessarily in LIGO, and that's, you know, perfectly fine.
The point I was going to make was relevant to this, the thing that you just said, that machine learning people are not really interested about gravitational waves. That is probably true. But one thing is that I strongly believe that there are many, many problems out there outside of gravitational waves where they have to deal with the exact same like overarching problem that we care about. Like, for example, if you take Emery detection, there's a huge amount of degeneracies that you're going to have, and parameter estimation is a nightmare. But if you then talk about, if you then look at, for example, drug discovery, which machine learning people do actually care about, then they also have to care about drugs which are present in like a needle in needle-like posterior, peak in the huge posterior, where most of the things that you search for is probably poisonous, and there's one drug in between. So you have things that are relevant, and the translation from what they're working on to what we are working on is also something that's pretty important, I think.
Yeah, I completely agree. Yeah.
And I'll add just one point to that, which is there's a good reason that they may want to work on the gravitational wave problem rather than the drug problem or whatever else it is, in that we have huge reams of open data and none of it has any ethical issues with using it. And so if you've got a new algorithm, it's great. You can go and write, you know, on it. And hey, you can find black holes at the same time, right? Like that's kind of cool. But it might help keep people around.
If there is no other questions, then I'm going to move on to one of mine. Trying to linking a little bit the previous session with this one. So classically, there are some very good reasons why the detection problem and the parameter estimation problems have been tackled from different ends. And I'm very aware there is a lot amounts of overlap, ever increasing overlap. What are your thoughts on, for the purpose of machine learning, is given the similarities in some of the techniques, is that distinction still useful, relevant, blurry? What? I mean, we're all patients, right? So I know I was saying that for you. Yeah, go ahead.
I can say something, but also I've been talking a lot. So if anybody else wants to. Okay, so that's a really good question. I think it is blurry, but I don't think anyone's actually tried it yet, which is that I think I mean, if you have like a huge amount of data, if you just take, for example, the embedding network, and you just use that as like a catch-all for searches, flows, whatever, and you use the same embedding network, I think that's a good strategy to employ, because then you can choose to just train one embedding net that's like absolutely enormous and have to do it once for the entire community. And then that embedding net can be used for searches, it can be used for PE, it can be used for whatever algorithm that you can come up with that I can't. So that would be my thing to do. I think that would be a good thing for someone to do.
Taking notes.
Yeah.
I would be worried about the interpretability aspect that we've been talking about a lot today, that if you're doing everything all in one, it's not, I think a couple of people have said today that there has not been so much work on looking at what happens with these machine learning algorithms when you're actually just feeding it things that it has never seen before and how you expect it to behave. So if you're sort of doing this in a search and parameter estimation way, we already have problems where we are sort of doing parameter parameter estimation on things that are probably glitches and they look really strange. And I think that problem will just get worse. Yeah.
I think a lot of the points that we've been talking about, it involves a large amount of data. And for problems that involve a limited amount of data, for example, there are many other considerations that you'd have to make there. For example, like if you're trying to learn some continuous transformation space, then there's a minimum number of points, that minimum number of discrete training points that you need there in order to actually learn that space. And if you have something lower than that, you're not going to learn it. And there's also the bounds of the space that you're thinking about in a parameterized problem. And the bound, if the bound is too small, then the method is just going to probably give you the mean of the value instead of actually learning the transformation that you want. So things like that. So are things like that more important, do you think, to focus on in the next few years, rather than just thinking about using in the infinite data limit?
Sorry, can you repeat your question?
Oh, okay. So like in the next few years, should we only be thinking about problems with doing machine learning PE, where we know that we have a large amount of data, or should we also be thinking about problems where you have a limited amount of data and there are lots of other issues that we have to deal with, where in the infinite data limit, you don't have to really care about those issues?
I think realistically, there will always be problems where we don't have enough data. So certainly that we're thinking about. If there's already a classical method that uses less data, as is sometimes the case, then you will probably come up against hard limits in terms of your accuracy and your efficiency in being able to use these methods. But as you said, there could be a really good test bed for looking at the sort of technical problems with implementing machine learning when you have small amounts of data, because I think it's worth looking into. If we want to have a more universal approach with using machine learning for lots more things, yeah.
I think this also comes back to the uncertainty quantification question. So, the size of your training data set is one thing that appears on the right-hand side of the conditional bar in your Bayesian posterior. So one example of this is problematic for us doing population inference. You want to compare, the gravitational wave catalog to some astrophysical prediction for what the population should look like. And the best we do for that at the minute is with population synthesis simulations, but they're typically expensive to run. So you have no hope of putting those codes directly into your likelihood function. So instead, what you can do is build an emulator or a surrogate with machine learning. But if it's expensive to run simulations, your training data is going to be small to start with. So then you want to characterize, okay, what's the uncertainty in my machine learning fit to the population synthesis code? So that's maybe one specific example on how you might do this in practice. There are many different ways to characterize the uncertainty, but again, there's lots of research in this in the Bayesian deep learning literature. It might be hard to be fully Bayesian in the way we are with parameter estimation because of difficulties in quantifying the uncertainty, but I think we can at least do something.
Just in case I don't misunderstand that, do you mean using machine learning to generate stuff?
Yeah, so you can build a machine learning emulator for a simulation code. So some kind of generative model or normalizing flow that also has the density.
Okay, so what do you think is more important, building a machine learning code as an emulator which generates more data for you, or a machine learning code that is able to get the same results on a lower amount of data? Where should the focus be?
Depends what you mean by get the same result, because being Bayesian really means quantifying all the sources of uncertainty in your likelihood. And oftentimes we're not explicit about what we're conditioning on when we present the corner plot of a posterior, for example.
It is time for lunch, unfortunately, so I have to break it. I would just say the usual answer is, it depends and do both. But the point I would make is we only have 1 hour for lunch. And you have to be back there at 2 p.m. You're on your own for lunch, and I don't think the room is locked. Go. Sorry. Thank you very much to the panel.
Thank you very much.
Just quickly, you can go and get lunch and bring it back here if you want to come and make the posters.
So regarding the population stuff.
We'll get it in about a week's time from the RAS, and I think they will put on their YouTube.
Hello. Yeah. No. Oh, yeah. Oh, yeah. Oh, just. Hey, hi. I think good to see you. How are you? Fine. Any questions? Yeah. You have in principle the same, not just even hierarchical, but the uncertainty of your machine learning. Yeah, it's actually pretty nice. Actually, they have it like monthly, something like that.
I think our table's the other side.
Oh, okay. Yeah.
I think so. I mean, I had the impression I was, and I saw people sitting.
Yeah, let's do that.
It's very fancy to read, like, old library.
It's kind of nice.
Oh, I'm still yeah.
Why didn't he have me on?
I took away it was my mic was. But I guess people can still hear us because this one's yeah. Hi.
Whoever's chair.
I mean, this is just where I can send messages.
Echt, ja, ik heb een hele goede band met hem. Dus, nog wat. Waarom zijn wij best? Ja, je bent gebleven. Ik heb een bachelor master met een PhD. Ja? Ah, nice. Ik ben zo op mijn boodschap over Cuba. Waar? Nog niet terug. Ah, je blijft weg zo. Best wel, ja. Ja, maar het is een duidelijk boodschap. Als ik even stiekem een jaar, maar het is een teruggebracht. Dus volgens mij is het een beetje een gezicht. Nee, nee. En daarna ben je van plan om blijven of probeer te blijven? Ik ben gewoon een beetje om te kijken naar wat er is. Ja, ik zie nu mijn laatste jaar van PhD. Ik ben nu nog een beetje zowel naar postdoc, maar een paar andere dingen. Ik zie buiten. Ja, dat vind ik wel lastig, dus, maar ja, ik zit een beetje kijken naar bedrijven. Ja, dus maar ik moet daar nog beter kijken. Het chill is dat het later postdoc zijn super. Ik kom even
Okay.
Hello.
Put the super chat there.
Excellent. Right.
You guys, everybody know, you're not too bad about it.
Have we got another one? Join.
No. Okay. Hello and welcome to the final session of today's meeting, which has been great so far. And this session is on next generation and future challenges. I have been roped into chair because there wasn't an official chair. But we have a great panel of Vanessa, Justin, Sebastian and Ian here who will give us a talk and take your questions afterwards. We have one sparkler slide, which I will move on to. There's next. Next. Yeah, press the green button. Oh, there we go. So it's Connor Muldoon. We have Connor.
Hello everyone, I'm Connor. I'm based at MMU, senior lecturer there. So this is just some work I did in the context of a European cost action on gravitational waves and machine learning. So that was led by.
Yeah, that's the green button on the clicker. Should move.
Okay. Yeah, so I'm a computer scientist. I'm not a physicist. So I'm kind of looking at the sensor placement problem. And I'm looking at it in terms of combinatorial optimization. So there are different types of objective functions you can have when you're looking to place where your sensors are. And depending on the type of objective function you have, different methods are appropriate for, for placing your sensors. So there was a lot of work done maybe about 15 years ago on submodular optimization. So if you can prove that your objective function has a diminishing returns property, you can just use a simple greedy algorithm and you can get a good bound on that and it'll be near optimal. So let's say you want to monitor the charge build up on the test masses. That might be a case where submodular objective functions would be useful. You can also use it for optimal Kalman filtering and for maximizing the Fisher information or the, say, mutual information of a Gaussian process will also work. But in future generation detectors, Newtonian noise will come more into play when you try to optimize it using a greedy approach. It doesn't perform very well. So meta heuristics are often used. So you've got differential diffusion, basin hopping. And what I talk about in the poster, and this is also coming out in the book from the cost action, is how you could potentially learn your heuristics rather than, say, hard coding them. Just using standard approaches from deep reinforcement learning, so sequence learning. The way I've implemented it at present is with LSTMs, but I think transformers could improve the performance.
Thanks very much, Connor. Okay, so who will be leading the discussion? Ian?
I think, yeah, I think.
Oh, your slides, yeah.
Slides are mine. So yeah, let me start off just because this is the final session of the day, just by thanking the organizers for putting together this session. You know, thank you, Anne, thank you, Mattia. Did Greg actually do anything? You sure? And maybe Greg and I guess Vivian and John probably didn't do any, maybe did a little bit, but you know, thank you for putting together a I think it's nice to see everyone together, having, you know, a good chance to chat, certainly get out of marking and all the rest of the rubbish that I have to do otherwise. So, you know, thank you very much. The second thing that I wanted to say is that I didn't want to give this talk. You know, we've had all these optimistic people talk about, you know, the future, you know, all the things and the prospects. And I said, look, I'm probably going to be a little more negative. And they said, that's all right. So, you know, I apologize. I will, you know, perhaps play a little bit to that. You know, I have worked in machine learning. You know, you have one of the papers I worked with before on convolutional neural networks. I think my first foray into machine learning was back in 2012 with Kyung-Min Kim, who's now in Korea, or he left Korea, I'm not sure. So, you know, perhaps I will be a little stronger than what I really believe, but to try and put across a sort of different viewpoint on the future challenges of next generation gravitational wave astronomy. So before I do that, you know, what are the challenges as we look forward? And really, what are we trying to do before we think about why it's harder in the next generation? So really, you know, we split this off into two parts. There was this, you know, an idea before that perhaps these don't need to be disparate. You know, why do detection and parameter estimation need to be different steps? Traditionally, they have been for computational reasons, but there's no fundamental reason, either with machine learning or through non-machine learning methods, that they need to be separated. But really, what are the questions we need to answer, right? What's in the data? How many signals? What are they? Are they supernovae? Are they string cosmic, whatever collapses? Are they probably mergers? Anything else? And this isn't just, this can never be a yes or no answer, even with numbers, right? It always has to be probabilistic. What is the chances? Because you will never be 100% certain. Even 150914, it might have 478 nines after that decimal point, but it can never be 1. And, you know, for the population modeling and applications that follow, it's always important that we quantify this. And, you know, any method must be capable of doing this. And this potentially is complicated when you have multiple signals overlapping, though probably more so, as was alluded to earlier, in the LISA sphere than it will be with ground-based detectors, or either today or going forward. With parameter estimation, really the idea again is to map out the possible values that a system can, that a signal can have. And it isn't, again, just an exclude region. It's not like it's in this box. And we have a habit of doing that in our results. We love to show 90% exclusion regions and nothing else. And that is just one line. And then it pretends that everything in there is the same. It really is, you know, you're mapping out a likelihood surface, P of having these parameters. It is, you know, and again, anything that's running this sort of has to produce that. So what is it that gets harder? And as you'll note, it's the same slide for both detection and parameter estimation, because what dictates what gets harder is always going to be the noise curve. You know, as we get more sensitive, this will dictate challenges. So what gets harder for detection? First up, for anything that's not a compact binary merger, detection becomes possible when we get to third generation detectors. So your bursts and your CWs and your stochastics go from being a, we're never going to see them right now, but we're going to run it anyway, to we might, and I emphasize might, actually be seeing these. You know, we are getting into interesting regions of parameter space for continuous wave signals. You know, we're beating into some of the theory space. It's always hard to predict the unmodeled searches. We don't know.
And we will start to impinge upon at least some region of predicted gravitational wave backgrounds, and perhaps we will see, background of compact binary mergers. Now, of these systems, only one of them has a properly worked out method for actually doing detection. That's the burst transient systems. Both CWs and stochastic detection there is hard. You can't time slide a continuous wave signal. If you time slide it, you get the same signal. So you have to rely on analytical models. And frankly, these don't work in real data. So it's going to be hard, regardless of what method you use, to convince someone that you've seen your first CW signal. And this perhaps gets a little overlooked while we don't have anything to see, but this may well be one of the biggest detection challenges in the next 10 years. How do we claim that? For compact binary searches, yes, the noise curve has gone down. They're louder. They have higher SNR. This is fine for detection. Louder is good. You just look at it and you see it. Worse is that it's getting broader. Yeah, this bit here is a problem. The signals are longer, and you can quantify bandwidth. There's a fancy way of doing it. It doesn't matter. But the bandwidth of the signals, the range of frequencies over which you're getting the power is longer. This means your parameter space is bigger. You need to search more. If you were doing this in a templated way, you need more points across your parameter space by over an order of magnitude to be able to find signals. Again, regardless of whether you use traditional or machine learning approaches, it's going to be more expensive to train or to search there. As you go to lower frequencies, the Earth has a habit of moving. This makes things increasingly complicated again, because you have more parameters in play. You have to know the sky location. These will become important. You can't just marginalize easily over parameters as we have done in the past. Finding BBHs then will be like finding BNSs now. So if you want your fancy new pipeline to work in the future, don't tune it on BBHs, I don't care. Show me it can do BNSs. Because if you show me your pipeline can do BNSs now, it can do BBHs then, when it's going to be important. BNSs become incredibly hard because they're now like almost like a CW source or something in between, where we really have to worry about it moving. And the very high mass systems, like your high mass IMBH, move into your previous BBH space, and they're easy. For parameter estimation, the biggest issue is your loud sources now, right? The cases for which you're going to get the most information. You might have systems with SNR hundreds. Our waveform models are not good enough for these. We need to deal with that. We need to quantify that uncertainty and work around it. So we'll have particular case studies that will be incredibly challenging to run. And we will, these are the cases for which perhaps we can get some of the most interesting results, cosmology measurement, perhaps with dark sirens, because of their loudness. But if we're biased due to anything being wrong, we have a problem. There will also be a huge bulk at lower SNR, which have similar problems to what we see even in the detection case. They will be quiet, and there will be a huge parameter space over which we will have to find them. And there may well be lots of other smaller bumps in the likelihood surface due to noise alone that we'll have to distinguish. Reducing the noise curve will probably result in a worse rate of glitches. That tends to happen. And we will more often be seeing signals overlapping with them simply because we have more longer signals. So we need to care a lot more about the effect of glitches overlapping with our signals. That kind of setting the scene, I will kind of change my gear a little bit. And I will ask, one thing we've kind of assumed, and kind of gets said a lot, we kind of begin to assume that machine learning is the right solution. So let me ask why. Why do we begin with this assertion? Machine learning and AI applications have been explored in GW analysis even as early as the late 2000s. Convolutional neural networks being touted quite strongly as the next big thing a decade ago. It's now 2025, and no machine learning powered detection or parameter estimation pipeline has been used in an LVK analysis. And that's not entirely true. Emily is running now, trying to detect low latency searches. Things like IDQ, glitch rejection has machine learning backends, but there's some other things as well. So why do we expect the next 10 years to be any different? Here's my sort of illustration of how machine learning is being sold to us. This here is a Bilby. A Bilby is the current parameter estimation pipeline that we use generally to produce LVK results. This is a dingo. The dingo is doing what dingoes actually do, eating the Bilby. And the dingo is a machine learning pipeline that has been developed to do parameter estimation. We've already heard about it. And, you know, the name is implying this, right? It was not an accidental choice of name. It really is saying, look, I'm the dingo, the Bilby is gone. You know, the Bilby has not gone, right? Dingo has existed for a while, and there is very little prospect of this happening. Wrong. So a different point, you know, is a focus only on machine learning actually dangerous, you know? And perhaps pushing back against some ideas like we should have a dedicated machine learning group and things like this, right? Why is machine learning seen in this way? You know, to be fair, there's a lot of scope for improvement, a lot of scope in both current detection and parameter estimation toolkits without invoking machine learning at all. We can eke out orders of magnitude in PE. I'm sure we can't with Vivian, orders of magnitude, definitely. You know, the search pipelines can be made more efficient. There are a number of approaches that are available to potentially solve the next generation challenges. What if we don't look here because we think machine learning is the future and it doesn't work? We would, you know, by default, we're using the machine learning method because that's what's there. But is it the right direction? Should we forget to do this instead of going on and exploring the improvements that we know are there? And in particular, what worries me, you know, we perhaps differently to some other areas, is over the last 20 years, we have accrued significant expert domain knowledge in gravitational wave astronomy. It's why our current methods do better than machine learning. You know, if we were starting today, sure, you'd go straight to machine learning, right? We don't want to understand and tune and develop these pipelines like we've done. It's going to be a waste of time, but that's not necessarily where we are. So perhaps the right question is, how can we apply machine learning without losing the domain knowledge? Not just applying black box algorithms, we don't know what's going in and we don't know what's going out, but how can we understand what they are telling us, what they are learning, what they're picking up, what they're identifying in our data? If they can tell us that, it can easily be, you know, it can be incorporated into traditional pipelines, vice versa, and they can learn from each other. So why do we always separate machine learning out from other analysis methods? And again, back to my example of a dingo and a Bilby. Dingo doesn't work. Stephen Green gave a nice talk down in Portsmouth, and one of the conclusions was dingo doesn't work. It does not produce parameter estimation posteriors that are comparable to Bilby. Where dingo does work well is where it constrains the prior. So dingo says to Bilby, search in this very narrow region, and Bilby goes and searches in that narrow region and produces a refined parameter estimate. What is not happening is that, in fact, the Bilby is utilizing the dingo, riding on it to more efficiently get where it needs to go and produce the results it always did. So, you know, this is what is happening. The Bilby, the traditional method, is harnessing machine learning methods to reach efficiency. It is not killing it. And I'll stop there. Yeah, sorry. So I guess we've got some, I do want to.
Yeah, have we got some more slides? So,
Yeah.
Thank you very much, Ian, for that. So next up, I think we have Justin or Sebastian. I think.
Yeah. No, it is you. Yes, just differently listed.
Sorry. Okay. Hi, everyone. My name is Sebastian Khan, and yeah, I'm going to talk about, well, make a case that machine learning models should be scalable, accurate, or not only scalable, accurate, but also probabilistic. And the sort of just little, some example I've got here is An analysis of a gravitational wave event shows evidence for non-GR behavior. Well, is it a breakthrough of fundamental physics, or is it just that your model is poor and or overconfident? And just a sort of toy example is we've got some simple supervised learning binary classification data set here. We have two classes, a blue class and a red class, two-dimensional feature space, but maybe it's much higher dimensional feature space. And then some example of some out of domain, out of distribution data. And a number of people already commented on how do we guard against things like this? But far too often, most people in machine learning or most machine learning methods are just point estimate classifiers that just give you, what is the most likely probability of what's the most likely class given some point in the space. And in this particular tree model, I've fit to this data set. It's nicely separates the two classes, but in this region over here where there is no training data, this green data is not used to train the model. It confidently predicts that it's going to be part of the red class, but maybe you got lucky, maybe these are red data points, or maybe there's something else. But if you just use the model on its own, it's way too overconfident. So this is where the probabilistic part of this statement comes in, where if you build a model of P of data, which is a model of your training set or your training data, some sort of generative model, then if it's got something like a likelihood prediction to it, then you could draw something like a likelihood contour or a boundary and say, okay, everything inside of this I've seen before, so I can trust my model here. But if a data point is outside this region, then it's out of domain, and it should have a higher uncertainty to it. Yeah, so that's basically it.
Hi. So I'm just going to briefly mention some things that keep me busy for the last 5 years, I'd say, which is related to ground-based detectors for next generation, so like Einstein Telescope, Cosmic Explorer, for which we've been, screaming very loudly that we should get money to build a very nice detector and do new science, which is true, of course, but not always looking at what the data is going to look like, which is more something like this, which is a fair change in paradigm compared to what we're looking at now. Right now, we have one event once in a while, and we have fair amount of time to analyze it. In the future, we'll just have events all the time, even if you focus just on compact binary coalescences. And this comes with a number of problems, which, of course, overlapping signals, the fact that, you've got also barely detectable signals that stack up, no time without signals, so better or worse access to your noise. And as mentioned before, it's going to challenge the waveforms. Somehow, if you want to do precision science, like you promised, such as testing GR, for example, or discover new sources, well, you do need to account for this to a certain extent, which could mean analyze all the signals or neglecting some of them, depending on what you believe, I guess. And of course, that means that you need to have analyses that are scalable, that can analyze, hundreds of thousands of signals at a time if you want to analyze them all, or that can marginalize over some of them. And currently our methods cannot do that, whether it's classical, even machine learning ones don't go that far yet. But we need to consider solutions, of course, because if you want to motivate the detector, you also want to motivate how to analyze the data. And so one of the solutions that's of course in the pipeline is machine learning. It's one of the solution, I guess, not the only one in this case. But it's a serious one because it's much faster. And so I didn't write explicitly questions here, but this sort of statements come with a bunch of questions. Of course, first, as this was mentioned before, is this the correct way to go? And if one believes that's the way to go, what do we need to do to actually get there? If we want to go in a world where we could just do everything with machine learning, how do we do that? What are the requirements we want? So this is just two big questions. I have, I think, at least 50, so I think I'll stop here for now. But the big picture here is really like, what are the next steps if we want to get in a world where this can be analyzed? And in this context, if we want to analyze with machine learning, what would people want to believe what will come out of our analysis?
Right. Okay, so the last bit, I'm sort of phrased over the question which was, will simulation-based or likely for inference methods replace traditional approaches? I'm going to give you the answer first. I think the answer is no. But we've heard a lot about them already, and they've been widely used in the community. And really, like, these libraries that are out there have made it very simple to implement these, even if you're not a deep learning specialist. And we've heard a lot about the advantages, specifically with the highlights of the fact that these are very fast, so it accelerates a lot of things. But I want to point out the second part, this bit down here, that there is a need for these methods also in the direction where we actually have very complex simulators that, for example, take minutes to hours to run. And we really want to sort of like try and learn something about the underlying physics from the signals that we are going to be detecting in the future. So I come not from the gravitational wave side per se, but from the nuclear physics and astrophysics side. So I want to really understand what's happening, for example, in situations like ultra-dense matter, and these things that people have been promising me for the last 20 years or so, that once we have a continuous gravitational wave, we can use that signal to then actually learn something about the fundamental physics. There's a huge gap in like what people have been like saying and developing models for, and how we're actually going to use that. So these inferences are really going to be only as good enough as the simulators that we have there. And people have been trying to sort of like figure out how these signals might look like for several decades now, but really don't have like reliable frameworks to actually predicting these. So I think there is an argument to be made that we don't just really try and work on the inference side and like have the methods ready there, but there's also a side that really like, I think we need to work more on the physics and try and really like build better models that we can then like feed back into this. And yeah, I make this argument specifically for the Newton star side, but this is true for like lots of the other areas where we try and want to use these signals. I'm going to assume that we're actually detecting them. Someone will make that work. But if we really want to use these to then like do something with them and not just determine things like maximum masses or like tidal deformabilities, but go further where we want to like measure like microscopic or local properties inside these stars, we're really like a lot away from that at the moment. So yeah, I'll stop there.
Okay, thanks very much to the panel for setting up the discussions. Do we have any questions to start things off? Up there.
I'm Konstantin Leider. I have a question because this was mentioned already a few times about this out of distribution claims. I mean, I realize these schematic plots are two-dimensional to visualize this, but how easy is it actually to identify something that is out of distribution if you like in 256 dimensions or something?
Really hard. I think I don't have an answer. I can just speculate on some things maybe. For example, like tree-based methods, they are often used on very high dimensional spaces, hundreds to thousands maybe or something like that. And what they seem to have really good, accuracy on some holdout test set, right? So how are they able to learn in such a high dimensional space? Maybe it's that they're not actually using the whole 1,000 dimensions. They're using, in this part, they're using these 20 dimensions. In this part, they're using these other 50 dimensions or something like that, much lower. So maybe maybe there's a notion of like effective dimensionality or something like that. And we have to try and use that somehow. And then you're not building a model in really high dimensional spaces, but just the dimensionality you need it. And that's like what like embeddings kind of do, I guess, in some sense, maybe. I don't know. But if you're learning on a lower dimensional space, that's easier, right? So maybe something like that.
Okay, thanks.
Greg.
Thank you. So firstly, thank you, Ian, for delighting everyone, I think, with your were they AI generated images as well?
AI.
I assumed you hadn't flown out to Australia to collect those images.
Yeah. No, Bill Weasel harmed in making of these slides.
So it's a really interesting sort of line of questioning. It's certainly not on next generation detectors, but that's fine. I think it was great that the panel took this in the direction that they wanted to see this discussion. Maybe if I push back on what you said in one direction, which is there is, and this is purely in the context of simulation-based inference. So of course, I think you're making the point more generally, but there are opportunities that the ML-based approaches offer. And so in particular, solving problems like non-Gaussian noise and non-stationarity, these kind of issues which we know are going to get worse, especially as we get to next generation detectors and we don't have the capacity to stare at every single gravitational wave event. That does seem to me like the real opportunity of these approaches. And so one of the challenges that I see is that the approaches have been sort of sold with great promise of reducing times down to seconds, and then also allowing us to solve this other problem. And as you say, we're still in the case where they're being asked to basically reproduce what the default analysis, if you like, are doing, and we're not quite there yet. But the exciting bit is what comes afterwards, right? Once they can reliably do that in cases where we control everything, they produce the same results, then what comes afterwards is the more exciting bit. And so I guess I would just offer that as like, there is a lot of potential for new things to come out of it afterwards. And I mean, that is what you were saying, but I just wanted to highlight that is a case where we may give up on these traditional methods once we can sort of simulate things properly.
Yeah, I mean, I think it is next generation, because now we need to be thinking and developing the methods for 2035 today. And that means that, the young people that we take on, we have to decide, which way they're going to work on, or they have whichever way we do it. Certainly not me doing it, and if everyone goes, oh yeah, machine learning is the future, which has become a bit of a narrative, and it doesn't work, then, was that the right approach? So really part of the question is, and why I do think I'm going to defend the next generation thing is, we have to decide where to devote limited person power to developing these methods. And do you put all the eggs into this one basket? Do you put all the eggs into the traditional basket? Or do you somehow try to put the eggs into one basket and stop calling machine learning its own thing on the side? It's a tool. It's a tool that can perhaps be used for this, and let you. I mean, one example where we've used it effectively, one of my PhD student graduated a few years ago had an application where we have a glitch rejection based test that's a chi-squared. It's empirical. It's not Bayesian at all. You'll hate it. But there's lots of parameters that can be used to tune it. And before, Tom Den, who was a postdoc many years ago, would have to sit when we tuned it, and he'd run it 100 times, and he'd look at the plots by eye, and he'd decide which one was better. And that's what we've used for the last 15 years. Whereas he went, well, look, you can just let the machine, you can the machine learning tool can run like a traditional method to get an optimization score, and then it can just try all the different things and find, the best one through some, I forget all the details, he does machine. But, and that kind of approach is sort of where I emphasize that I didn't have an image of a Bilby with a gun and a dingo on the floor, right? Which I could have done, right? Maybe that would have been slide 3, right? And then we back up a bit. But, the Bilby was riding the dingo, okay? The Bilby was harnessing the power of the tools available to it. And perhaps the Bilby's riding not just the dingo, but perhaps he's riding the old, I don't know, what's an old horse, looks a bit like me, that's been around for decades and, still perhaps providing some use, but he's riding that as well. But the Bilby is using all the things available to it collectively, rather than, the dingo trying to replace all of them. I think I've pushed this a bit.
Can I also add one thing? I think this, like, you don't know though where it will be useful or not. I mean, I think you can't predict these things, right? Like, it's very difficult to foresee what's going to happen in 10, 15 years or what these signals actually look like. So like, I think we should, as a community, like try and like branch out as much as possible and like try and like get us to a position where we could easily adapt to what's happening. And I think I think as a community it would be silly to like completely rule out machine learning as a possibility for that. So I mean, it does take time. There's a lot of things that are happening very quickly. And to like be able to like quickly sort of pivot in one direction, I think as a community, we have to be able to like use these methods and like be included in the development and push that in that direction.
Okay, I feel somewhat compelled to say something for various reasons. Okay, so first I want to say to everyone in the room, okay, Dingo is a playful name for Bilbies. It was never our intention to say that we are going to completely replace Bilby in the gravitational wave sphere. We have a massive amount of respect for everyone that works on Bilby. I will just say all of our data conditioning is done by Bilby Pipe. The likelihood we had to implement separately for a very special reason. But so much of the functions that we use from Dingo are because of Bilby. And I think it's very safe to say Dingo would not exist at all in any capacity were it not for Bilby. So that's just the first thing. So it is not our goal.
True if the dingo's eating the bill.
Yeah, that's true actually. Yeah, so that's not to say that, you know, we want to replace Bilby. It's just a playful name. Okay. The next thing is with regards to why it's been 2025 and why is Dingo not in use. So I think this comes a lot down to more timing than the actual status of the pipeline, which is that it's true that actually for O4A, we reviewed Dingo, right? But we didn't want to use it, and it wasn't our goal to use it for the RODA or for production analyses because we wanted to build trust, right? We wanted to show that even if we have a reviewed pipeline, can we show that it still produces on the fly correct results that are in agreement with Bilby, right? I mean, that's how you build the trust, right? And talking to some of the Bilby folks who people can correct me if I'm wrong about this or not, that was also the case when there was a transition from ML inference to Bilby, right? One had to build trust in doing that. So that's been our sort of goal in O4A. Now in O4B, we are, you know, thinking of trying to extend that and, you know, trying to aim for some of the production analyses. And we've been in discussions with the PE chairs about that. And the last thing, there was one last thing that I was going to say. What was the last slide again? Okay, yes. The Bilby riding the Dingo, yes. So I don't agree with the statement that Dingo does not work. And I know you said that to be very provocative, which I actually like. I like very provocative things like that. I will agree with the fact that I would not use Dingo on its own, probably ever, right? I would always use Dingo plus some sort of classical algorithm. Now, why that has to be Bilby, I don't see why, like what that has to do with it. I mean, it could just be importance sampling, right? Or it could be running MCMC after your proposal, right? But I do think you should use both if you can. And yeah, again, Dingo is not trying to replace Bilby. That's not our intention. If Bilby people want to work on Dingo though, I'll be very happy. So I don't know if maybe when Bilby's evolved, they turn into Dingos or something, or maybe the other way around, I don't know. But yeah, okay, that's it.
Could I ask that, other than, you know, being provocative, which
Yeah.
as you say, was deliberate, was there anything I wasn't sure you disagreed with me.
Did I disagree? Well, maybe not really. I mean, the one thing, it was a bit provocative. I would disagree with the provocative points, but I think the timelines thing is a bit, that's probably the one point. But other than that, I mostly agree. I mean, I do think you need to use some sort of classical method with machine learning, no matter what you do. Yeah, but yeah, good points.
Yeah, I mean, I want to at least defend, you know, I worked with Shulkopf before Dingo was a thing, and trying to realize at least the AI that putting those two together was useful. So I'm not intending to completely destroy Bilby or anything, Dingo or anything like that. I really get, you know, certainly the work that's come out from that has been very impressive.
So Lucy and then Greg, unless Greg has to respond.
So I guess this is what we're converging on anyway, but I was just going to say that, like, I agree that classical plus machine learning is a great thing. It's also, especially for the way that we're interpreting results, like new physics and things we can't do at the moment with classical algorithms aside. We're I mean, I'm speaking from the viewpoint of waveform development, that this is something we're doing very successfully already, that we know how to build surrogate waveforms. We're just using machine learning to do the bit that we do already know how to do, but machine learning is solving the problem of doing it much faster. So is that sort of a good starting point for us to have, that problems that are already solved, we just use machine learning on them anyway to maybe do them faster or to do them in a different way and see what that gives us?
I mean, I think the answer is yes. So I think the problem that I wanted to highlight earlier is like, if you already know how to build a surrogate model because you know the underlying like model, how you build a waveform, then you can do that. But I don't think that as a community, we have really figured out what the signals will look like for the next generation. So if we want to like, and just because there's so much more physics, I mean, if you think about the signal, like the physics that go into like any kind of coalescence signal, I think they're very limited. I mean, I don't want to say easy, but there isn't that many free parameters that you can eventually vary. But if you think about it in terms of like actual physics, like what you have in a neutron star, if you want to model like some kind of collapse supernova process, there's so many different things that you can tweak. If you want to build a surrogate model, you at least need some understanding of what the physics really look like. And I think we're not there yet to even build surrogate models for those. So yes, for the signals we already have, I think you can do that. But for like looking ahead, I think we're like lacking quite a lot on that front. Yeah, and I get sometimes a bit pessimistic about that. But yeah, I think there needs to be some more model development happening. So just to like as a side, so for the population synthesis for the neutron star isolated population that we've been looking at, we've only just figured out really how to develop the actual the physics, and like it involves differential equation solving. So like the whole simulator takes like an hour to run. So one of the things that we want to do is like build one of these surrogators, but it's taken like quite a significant amount of time to actually figure out what the simulator really looks like that we then want to actually emulate. And once you have that, then you can go from there. But I think you can only like build an emulator if you have some understanding of what you want to emulate. And we don't really have that yet for lots of physics.
Can I add something related? So another thing that's related to that, and it's a problem as well when you think about future detections, at least for me, is that, and we've said it a couple of times, you always want to compare with something you know how it works, which is generally a classical approach. But when you enter in a paradigm where classical approach just don't work, and your only solution is machine learning to a certain extent, you know, if you're in that paradigm, can you still sell your results to a certain extent? Or even how do you validate them? I think that's also something that for future data like 3G detectors, we need to start thinking as a communities. How can we move in these edge cases? I mean, Greg was mentioning cases where they offer new solutions. If these new solutions are different enough that classical methods don't work, you still need to trust them. And so you need to build some sort of agreement on a standard, let's say, that your analysis or your framework needs to meet for it to be used. And I think it's something that we have touched a bit today, but maybe not that much, is what happened when classical comparisons are not possible anymore. And this can be the case if you need to do, for example, you know, global analysis with tens of hundreds of signals, and machine learning does it for you. Well, maybe you can offer one comparison if you're lucky, and that's it, which is probably not enough to say much. So how do you work in that case is also something I think needs to be worked out in the coming years if people really want to pursue machine learning based solutions.
I think Greg, then I think Matt's up there.
So that perfectly sets up my question, because I think I would be very disappointed if in 10 years' time we look back and all that machine learning has given us is speed ups. It will be very boring. So I want to ask the panel and also anyone else in the room, what examples do we currently have where machine learning is doing something that we could not do otherwise classically? And I'll start you off with one, which is that all gravitational wave data right now is cleaned using a machine learning approach that, as my understanding, gives you about 3 megaparsecs improvement in the range of the detector, which isn't massive, but it's not something, you know, it's not nothing, and you couldn't do that in a different way. That's my understanding, at least. Ian can disagree, but please disagree.
I disagree, but I don't have enough detail. I disagree that it couldn't be done classically. The question is whether it would be worth the human investment to understand that problem in sufficient detail. But the machine learning is picking up some feature in the data, some correlation between auxiliary channels that when cancelled out, removes noise from HFT and hopefully, although that hasn't always been the case, doesn't remove signals from HFT. I do not believe there's any fundamental reason why that can't be done without machine learning.
Obviously here, we should all clarify, when we talk about machine learning in all this discussion, when we talk about artificial neural networks, MCMC, nested sampling, linear, like fitting a line is machine learning. Reduced order models, machine learning. Sorry, carry on.
Where do we draw the line? Other things that we what are we using machine learning for right now in production?
Waveform models. So Patrick Sutton speaking. I would just like quickly to advocate for speeding up as a really good thing. Not just because it's convenient, but most of you may have seen the headline this morning that in 2024 was the first year in history we've passed the 1.5 degree heating globally, right? So we are actually literally killing the planet. I mean, it's quite possible 100 years from now, people won't be able to sit in a room like this and have this discussion because civilization as we know it will have collapsed. So well, that's extreme, but it's possible. It's possible that we'll be in that situation. Just reducing our computing use, just for figures, the computing use of LVK, if you just divide it by all the LIGO Virgo Cogra members, it works out to about 50%. So my personal contribution then from LVK computing is about 50% of the average carbon dioxide load. So I think it's 5 tons per person in the UK and another 2.5 tons for the computing we do for being in LVK. So, if we could reduce that, I think that's itself a worthy goal.
So I think there's a couple of things that come to mind regarding what do we do now with ML that we couldn't do otherwise. One is analyze or do parameter estimation with NR-based waveforms. So I would class the NR surrogate as a machine learning based. It's not a deep learning based, but you couldn't do parameter estimation with NR. And this is, one, you're interpolating the parameter space, but you're also speeding up a waveform generation that takes months versus sub-second. Another thing is doing, and I don't think this is particularly common, but doing astrophysical inference, so measuring astrophysically relevant parameters for the progenitor formation of sources, which again, because the simulations are too slow to put directly into a parameter estimation pipeline, you need some sort of machine learning emulator to do that. So I think those are 2 practical examples.
So I was going to go with slightly sort of related to the previous point, actually, on speeding up. One of the questions I always have with a lot of machine learning approaches is whenever we go and train some MPE, we rent an A100 for however many hours, and that costs however much dollar amount. And then we tend to compare to whatever essentially free CPU resource we have lying around. So once you actually amortize the dollar cost, maybe I'm speeding it up, but am I making the calculations cheaper?
I mean, for the cost in dollars, I don't know. There have been comparisons for emission, like CO2 emission, and that accounting training is generally less, at least for parameter estimation, less important than if you actually run CPUs. Because you generally also run many CPUs in parallel rather than one GPU for longer. So it has an effective benefit in the end. Of course, you factor in the price of a GPU, etc., in terms of dollars, that I don't know on top of my head. But to come on the question of global warming, there, yes, it's helping. Especially, if you put whatever we're doing now is basically baby work compared to, if you get one signal every few seconds, right? So when you put things into more and more signals in perspective, the gain is going, I think, to be really important.
I mean, I do absolutely buy that. And I mean, the power of amortized inference is kind of obvious. But in order to say that you're actually using less power, you need to stop retraining it at some point and be happy with whatever you have. And given the kind of exploratory nature of a lot of these analyses, obviously we're not doing that. We just keep retraining and retrain, you know, we keep trying different things and running for another 60 hours on an A100. You know, there's obviously a promise that it can be amortized, but are we going to realize that effectively? Would be my counterpoint to that in terms of global, you know, if we're thinking about emissions, right, you have to actually use the amortized part.
So my understanding with modern data centers is that the dominant CO2 cost is not the running costs at all, but the construction. So your fancy new A100 is gonna be whatever, whereas, you know, traditional methods running on some old CERN cores that aren't being used right now for Atlas analyses are, you know, effectively zero if you believe in that accounting.
And I mean, I think Lucy mentioned this earlier. I mean, like for lots of these SBI methods, what is computationally expensive is producing the simulations and like actually your training data. So like training itself might take you like a day or two, but to produce like the data set that you want to get, if you don't, I mean, if you have a neural network that emulates that simulator, but like if you don't have that, then it might take you like months, years. I mean, in cosmology, like we have like a couple of large scale simulations, right? They take years to run. So like if that's like versus the day of training, you have to kind of balance where you get your training data from, which is always a big problem for lots of these problems.
And I mean, I do kind of, yeah, I agree. Like, I think, yeah, I just think it's interesting. Certainly from the point of view of writing papers, there's a temptation to make a very apples to oranges comparison when you're using very different hardware. And that's a slight bugbear of mine with a lot of SBI work, right? Because, yeah, if you divide by dollar cost, certainly then things don't look quite so pretty. But if you do realize, yeah, you know, a data set that you are happy with, that you've simulated, you've sunk the cost of simulating it, and then you can retrain. And yeah, that makes a lot of sense, and I think is a good route to go down as well. So I'm not against it, but it's just interesting.
Yeah, I think the thing about the speeding up is really great and useful, especially when you're using EOB. But I wanted to make actually a slightly different point. So like up until recently, I would agree with you that, I mean, like other than speeding up, there isn't much like extremely useful things, although speeding up is in itself useful. But I will say that at least in the case of NPE, it operates in a, I think, fundamentally different way than MCMC or nested sampling does, in the sense that you are learning the mapping from the data manifold to the posterior manifold, rather than basically climbing that surface. And I would expect, and from all the tests that we did, we pretty much found agreement with Bilby between Bilby and Dingo results, right? The 90% intervals were similar, the evidences were similar, and so it was all fine. Until recently, when there's one event for which we find different results in O4A. And I don't know exactly what's happening yet, but I think that's the case where it actually becomes useful to have a sampler which runs on a fundamentally different operation scale than nested sampling. I don't want to make a claim on which one is correct because we are still investigating that. But yeah, I think that's the case where it can be useful to have a cross-check.
Yeah, so I wanted to change topic a little bit. The first thing I wanted to reiterate the point that Ian made, which is that we should all be considering machine learning as a tool, one tool among many. And it's not like machine learning has to be its own thing. And I agree that, you know, within our groups of parameter estimation and searches, we don't need ML-specific subgroups. It should just be one extra thing that people have expertise in. And then I also wanted to bring it back to sort of surrogate modeling and next generation inference, which is that, so one of the key sort of theoretical issues we have is developing waveforms. And I hear that for next generation inference, even numerical relativity isn't at the level of accuracy it needs to be. There's some preliminary work in using machine learning like super resolution to improve NR simulations. So I guess my question is that, can some ML techniques help us along the waveform development side as well?
I don't know about super resolution, but I'm already skeptical about it because, well, it goes back to the trust issue, I guess. I suppose if you can show, if you have a proper test data set where you can show me like, you know, the machine learning model is doing what you say it's doing, and then also you can compare it against a classical NR approach, then I'll believe you, I guess. Yeah, that's all I got for the super resolution stuff.
So I think, I don't think that is possible yet, but machine learning tools and like the whole framework to basically resolve fluid motions on smaller scales is something that people in the CFD community, computational fluid dynamics community, are really heavily working on in the last 5 years, I would say. There is a lot of, I mean, the community is huge, that is really trying to like use these methods to try and resolve physics on smaller scales. And yeah, combine that with traditional approaches of solving differential equations to really like try and model these systems. And I think there is some, I mean, I'm sure this will happen, that the NR community will pick up on some of these tools and try and actually push how they solve their differential equations essentially. But as far as I know, I haven't seen anything on that in the numerical relativity community yet. But they have, yeah, so on the computational fluid side, there is lots of stuff happening on that front to try and really push this and how effectively they resolve certain features. So I think for the numerical relativity and how they solve differential equations, that will help as well.
That's really interesting to hear. And I think, again, it will be a combination of approaches, not just the ML or the classical approaches alone. So for the super resolution, for example, you know, the training is guided by satisfying the constraint equations that you need to evolve during your NR simulation. So again, there are some sort of sanity checks motivated by the, you know, classical theory, which can help.
Yeah, so there's this whole field of physics-informed neural networks. I don't know if people have heard of this, but it's essentially like putting physical boundary conditions of any kind of system into your loss function. So you're sort of like doing the standard optimization that you have with an additional boundary condition where you then try and solve these differential equations. So people have like tried to do that on the astrophysics side in very simple problems already. But yeah, people are really trying to like model more complex systems with these kind of approaches as well. And I think that's probably another area where you could see people make use of these kind of tools. But again, they always sort of like come back to the classical methods, because you need some kind of like initial data, or like you need to benchmark these against some kind of simulations that you already have to see if this is actually working.
Any more questions in the room? Oh, Vivian.
Sorry, I waited until there really wasn't. No, I tend to rant a bit. That's, no, just I do find I agree with a lot of the points from Ian, and one of which is, and I know this is going to sound like a old grumpy person, but isn't all this machine learning thing just interpolation with a new name? Kind of, and there is a little bit of that in the sense that I don't think it's fair to compare. There is detection techniques, parameter estimation techniques, and machine learning techniques. No, that's apples and oranges, right? It's just machine learning is a certain class of techniques that can improve a lot of things, and I think the reason everybody has different opinions, and as Matt was saying, by machine learning we mean deep neural networks, for instance. Is that really what we mean? And do we consider reducible quadratures or building surrogates, machine learning, etc.? All of that is a little bit the semantics, really. What, in my mind, does make it, there's a lot of reasons why it would be different. And the progresses of the field and the kind of thing that you can interpolate now with modern deep neural networks is truly mind-boggling, and it's not something that we could interpolate before. And we've all seen it work. So that there is a step change in terms of what it's able to do. But there is also, we're not developing gravitational wave analysis techniques in vacuum, right? There is a lot of other fields around that are developing a lot of techniques. And while we do have the domain expert knowledge for gravitational waves, we probably want to use and leverage all of the improvements in relevant algorithm from a lot of other fields, some of which are dedicated applied math, machine learning developments, but also other fields that have solved similar problems or problems that can be phrased similarly, and they've done a lot of progress. And what might make machine learning somewhat different is that, especially recently, it is a field that has, it is an application, a method that has had so much effort worldwide put into, from hardware, software, documentations, learning, teaching, grant success rates that include machine learning in the name, etc., that this is something that, of course, we as a field do want to use, and whether it is the right algorithm that would exactly solve our problems, I probably think that if the only mathematical problem that was relevant in the world was graph-natural astrophysics, we probably would not have developed it the way it is. Machine learning would not have existed the way it is. But because it exists and it works so well and it's so easy to test things and it's so easy to leverage huge amount of hardware that has been custom made for that system, not by us, obviously, then it makes sense to use it a lot. And so that's why I think machine learning is a little bit different from all of the others, interpolation techniques, and we want to have that as the toolkit. But to Ian's point, this is maybe my vision for why it is a little bit different from, I don't know, FFT as a technique that we use all the time. Another way that it is a little bit different is also because, well, it's new. And we don't really know which way it works best for our case, and presumably in a few years things will be very different. And by the time the third generations actually comes in, the field of machine learning, if it has the same name, will probably be very different. So I guess my point is a little bit tangential to all of those. I do tend to agree that ML is not in its own right, comparable to detection of parameter estimations. It is a tool, but I would argue that especially recently in the past few years, it has some promises that are definitely worthwhile having the discussion sessions at workshops about specifically, and I wouldn't necessarily advocate we do the same for all of the other methods at this stage. But this one is clearly one that has some impact. That said, yeah, I mean, very clearly, I think it's almost nonsensical is probably a little bit too strong of a word, but I don't think it makes a lot of sense to talk about solving the graph-natural problems just with machine learning. To me, that sounds a little bit like saying we're going to solve the graph-natural problems just with the Fourier transform. No, but yes, I mean, it clearly it's in it and it's core, but no, it is a tool. I guess that's. I know this is a bit ranty. I did warn you all, but it helps me frame that usage. And so I can totally see, depending on how the rest of the field of applied mathematics and other of the many, many fields that have time series and that analyze time series, which way they go, maybe we will stumble on something that they will find useful. Maybe more likely there will be a lot of algorithms developments that they do, some of which will be applicable to us. And a lot of this will fall into machine learning just because there's so many working on it. And we definitely want to be aware of what it is. But yeah, I don't think it can possibly be developed for gravitational waves, not very much linked to our existing techniques, and hence the picture that you made at the end. I mean, as Nihal was saying, Dingo uses Bilby as a library through and through, and PyCBC does use machine learning in a lot of different ways, and I would argue, I don't know, it depends a little bit on your definition, etc. But those are maybe perhaps some of the points for why machine learning right now is a little bit different. But 5 years from now, it might be a brand new different things. And I want to study the universe. I will use whatever tools available, especially the ones that work.
Hi, my name is David, and I'm from a different field. So I hesitated to make any comments at all. But I come from a field of physics that is perhaps more. We adopted machine learning at a greater level. And I think 15 years ago, we were at about this sort of stage in our adoption of machine learning, where if you wanted to publish something using a machine learning technique, you had to have a more traditional technique showing that they agreed. Then gradually the machine learning techniques became more and more powerful, and it now enables us to do things that would be absolutely unthinkable to 10 years ago. I'm amazed at what we can do. And so my subject area would be absolutely impossible without it. Just to kind of reassure Ian, what we found is you can't use them as black boxes. You have to have the domain specific knowledge, and in fact you find that it enhances your knowledge. Most of the time when you first start training your machine learning algorithm, it doesn't work, right? Or doesn't give you any improvement or anything. And then you actually look at the output and you understand why it doesn't work, and you build it into your loss function, or you build a different architecture or whatever. And you build on this. And now I'm not saying that the domain I come from you'll exactly match that developmental history, but we've learned a lot from doing this, and I wouldn't be surprised if you go down a similar path. Again, as I said, there's so much work being done on this. We take often leading edge machine learning algorithms, and we adapt them. We don't reinvent them, and we use a variety of hardware. We use obviously a lot of GPU time. Somebody mentioned FPGAs this morning. We use a lot of FPGA time. And things like this. But ultimately, the physics that we've been able to do has been vastly improved by the use of these machine learning techniques. So there is potential there.
Yeah, thank you for that. I mean, I think, yeah, it's good certainly to give a counterpart to my cynicism. I mean, as I said, I was somewhat deliberate given, with a room that's promoting this, and would certainly like to see something, more useful come out. Yeah, there is a backdrop of this is always going to revolutionize, and here you are 7 years later and it hasn't yet happened. But what I would really like to be able to do is see more information coming out, right? What have you learned? What is the black box telling you? What have you learned about our data space or parameter space that underpins this? And can that be extracted and sort of, if we understand weird features in the data space, can that go back to say modeling or wave and try and tie all of that together rather than having it as a method that just sits aside and we just trust what comes out of it.
So I think going back, say 15 years is about then, we didn't need the machine learning techniques, and I may be wrong, but it strikes me that you're not at a state in the community where you absolutely need these techniques to make a revolutionary change in the science that you can do. It's only when you're at that stage that you really need them that they come into their own. And the thing about domain specific knowledge, you look at something and using machine learning as a tool, I think that's exactly the right way to look at it. You actually learn from why the training isn't working, or why you learn things you never thought of before. So using it as a tool in that way, I think it'd be very helpful to us, at least.
Brilliant.
I do have a comment on that, because I agree we don't need it right now to do the science we want to do with LVK. But I do think that we need new tools and better tools when we think about next generation detectors, because some of the tools we have don't work. And so I agree that the process of learning new things by developing machine learning is very important and interesting on its own. But to a certain level, I guess, when you really want to already, fix plans for future detectors, your data can also serve as a feedback loop. Like what you get out of your data, depending on how you configure your detector, can serve as feedback loop building the detector. And that does require these tools let's say, as soon as possible, because, you know, if you get them only once your data is there, well, you just have to deal with whatever the detector looks like. So for me, there is, I won't say big sense of urgency, but there is some level of need as well in better analyses. That being said, I'm not saying we should just use pure machine learning. I think we could get away with hybrid approaches as well that are not pure black boxes. And this last point that strikes me a bit is, to me, it's a bit like machine learning is a different thing from the rest because we decide to make it different to a certain extent. It's a new technique that came in, but, you know, there were other new techniques that came in the past. And at that moment, they were also a bit curious, a bit mysterious, and, you know, everyone was just throwing them out because it's sexy. But to a certain extent, that's sort of how we decide to see it. If we sort of, you know, put it in our standard tools and just put it in parallel with the rest, then, you know, it is indeed just another tool. And so I think all this sort of replacing thing comes a bit in because it's new and people get excited about it, which is very good. But on the longer run, things are going to calm down just because it's going to settle.
Yeah, I completely agree with what Justin said. And also like a kind of practical example, which is that, like, let's say in 2 years' time, there's now an eccentric processing waveform model. Okay, I don't know exactly when that'll happen, but okay, maybe in 2 years it'll happen. I think that's reasonable. But I'm also not a waveform developer. That model is for sure going to be very slow, right? And in O4A or in O4, we have maybe probably at the end 200, 300 events. How are we going to analyze those events, like the entire, you know, catalog of those events, using an eccentric processing waveform model? And I think that's super important because we saw in O3, we had a very slow eccentric waveform model, and we weren't able to analyze all the events. And in my opinion, we sort of missed something, right? So I think that's another practical example where you do need machine learning techniques if you want to do new science, right?
I was just gonna, I think it's a really good point, but I think it's also, it's not guaranteed that your current ML methods will be able to fit the eccentric processing waveform parameter space as well. So you may even need to do more work on that front, even then.
Yeah, I agree with that.
I mean, is there a question behind that of, again, what do we consider ML and where is the cutoff? You know, one might argue that if one can train Dingo to do parameter estimates over the entirety of this waveform model, that one could similarly train some form of surrogate to produce that waveform. And you know, I've probably not included that in my definition of ML, maybe unfairly. I don't know. Someone
would
give me a good sense of where that lies, but
I think that's up to other people.
Right, we've still got 15 minutes left of discussion. We probably want to have a bit of wrap-up time towards the end. Are there any more questions? I was going to ask a question to the audience, just in case there's anyone that has any information on this. So we've heard a lot about detection and inference and that sort of thing. Does anyone know if there are applications of artificial neural networks in, for example, detector control for Einstein telescope or TDI for LISA or something like that, that's more detector based?
Yeah, so I know that, for example, in NICHAP, they're using machine learning to improve their simulation framework for the detector itself. So to find optimal solution of configurations of mirror placements and, you know, laser and things like that. So they do use it as well. It's not my domain at all. Just know it because I happen to have spoken with some of them recently. So yeah. And also for noise.
And then,
I know also there's been work related to, sorry, this is Jess, by the way. There's been work related to, on the anomaly detection side, of understanding detector stability, which has been done by a few different people, I think, over the last few years. But to sort of maintain detector uptime and sort of identify periods of detector instability, and then hopefully trace that back to some sort of source of where that comes from using auxiliary channel data. But I think there's like so many different avenues to go down on the detector side.
Yeah, I think it's Joe Bailey here from Glasgow as well.
there's a few different things. People have applied this in lots of different ways. One of them being suspension control, so just controlling where your mirror is pointing, but using sort of a reinforcement learning style thing to do that. And there's a little bit in, well, which we're working on at the minute, which is in sort of designing future mirror coatings using machine learning as well. So there's a few different applications. There's probably much more than that as well. That's just the first two things that popped into my head.
Any other hands up?
Well, on that line, there was recently a paper on locking GO600 fully with reinforcement learning as well that seemed to be promising, and that's being considered to push further for ancient telescope, for example. So used quite a bit, I guess.
Vivian has the mic.
Yeah, but this is a totally different question. So it has nothing to do with that. So if someone else has then a question for the audience, because I've heard it before, and now with the discussion with next gen is very relevant. And from Nihar's example, clearly, if we spend a lot of time training some sort of deep neural networks model that will work for a while, it was very expensive to train, and then a couple of years later, someone computes the 7pn term, or there is a reason for why now we would want to update that model. Has anyone done, what are the audiences here experiences on getting an existing neural network and enhancing it, adding it, starting from that to train on new data that might contain new physics or even a new parameters? Or will we be into a models where we train the generic very well neural networks, and then someone can add their own testing GR modifications on it, but they don't need to train it from scratch because there is enough. I'm saying that because some of the examples that Nihar just gave, one of the issues that have been encountered with, for instance, building Russell quadrature or surrogates is that they do get out of date at some point. You get a new model, and it's not always been clear how to avoid redoing the calculation from scratch with the new model, which has a lot of issues. And I'm wondering if there's people have first-hand experience on this kind of doing that, but with a machine learning deep neural network training.
I mean, for me, there are several solutions that you could think of, but a classical thing that's often done in machine learning in general is transfer learning, right? You can have something that's pre-trained on one problem and transfer. I guess, for example, for 7p and older, yes, it brings new stuff, but it's not going to be that different either. So you have already a good basis. Another approach is for example, having a generic model that's trained, and then for a specific event, retraining on an event specific basis, where basically that training would go much faster than it would be maybe even a few minutes, depending on how efficient you are, but it would still be able to extract the appropriate information for what you're doing. So for me, yes, I don't think that because you get an update, your model is necessarily completely wasted, let's say, and you can use one to build on another, and which I think makes it even more important to take time to develop things well and see how you can then reuse them.
I was going to say that in waveform modeling, we sort of do this in a way, because when you build a surrogate model, you don't build a model of the whole waveform all at once. It's always modular. So if, for example, there's improvements, I don't know, say to build an eccentric precessing model, if this works, then there's very clear avenues to separate out the eccentric part that we don't yet know how to build properly with precession, and then processing waveforms that we already know how to build those in modular ways. And so if there's improvements to just part of those things, then that's a thing that we know how to do. Add your example of like adding in extra PN terms, I guess then transfer learning and things like that might be more applicable, but yeah.
Oh, yeah. So also on the SPI side, not so much on the waveform side, I actually think it's quite tough to do the transfer learning just like on its own, because at some point what we tried doing was training a model with just training a line spin EOB model and then reweighting with XPHM model. And that works sometimes, but the problem is you sort of lose your mode covering, right? Like the whole idea is that if you're always training in distribution data, then you should be mode covering. So that's the first problem. The other problem is that if the size of your posterior is expected to grow after you've like included more data into your transfer learning process, then the loss explodes. Right, and we saw that empirically. It essentially what happens is that the posterior like begins shrinking, and then you add data, and then it expects to grow much larger, and then you can imagine like a large importance weight getting stuffed at the very end because the posterior has grown broader. So the ways to kind of get around that is that to keep the embedding the same, but to retrain the flow. So that's one thing that people can try. I think Michael Pure is kind of working on that, but he's just starting. The other thing that you can try and do is edit your density estimator to not be just a flow, but to be like MCMC, for example, where then you don't need to necessarily have mode covering, but you still have an efficient proposal. Like EOB and XPHM aren't always that different, right? So even if it's not mode covering, the fact that you initialize your MCMC samples with your flow makes things faster. But actually, I think it's a challenging task overall. Oh, and the last one, which is the variable number of dimensions. And that's, I think, a super interesting problem, which is that, like, let's say you train an eccentric model and then you want to add precision to that. Like, what do you do? I don't really know. Like, maybe there's some other algorithms you can do, but one way is if you're going from a higher dimension to a lower dimension, you just mask the output, right? And so you have a variable output dimension by just masking the output dimension. Okay, sorry.
Okay. Oh, Lucy up there.
Sorry, I just thought of another question. Related to sort of future work in 3G, are there any problems that you think our classical methods can't solve, but you're also skeptical that machine learning-based approaches won't be able to help with either?
I mean, maybe I can try. So I don't really have an answer to that, I guess, in top of my head. I guess, you know, the problem with the question, let's say, is also that what we're going to face with is not clear yet fully. But I think things like population analysis, even for machine learning, will be challenging because you have so much data. I mean, there are ways through. I think usually people present it quite positively. It's not necessarily where I'm working mostly on, but I'm still a bit skeptical on that level. You know, if you really want to do a population analysis with thousands of events, are you still going to anything that's tractable or trainable on a machine learning level? I think that's maybe one place I would put some note of caution. And another one that's, I think, not related to machine learning, but to our interpretation of it and some discussion we've had here is for people that let's say go the whole let's do everything with machine learning road. If tomorrow some machine learning that tells you that there's deviation of GR, are we really going to buy it? You know, especially if it's, again, a hierarchical analysis of a lot of events that cannot easily be reproduced with traditional methods. Like you cannot just reweight somehow with important sampling or something. Are we really going to reach a conclusion, or is it just going to be a hint and something that remains open? These are maybe more the questions I would try to address or think about in maybe even more philosophical terms.
Yes, even generating a waveform model that is accurate enough not to dominate systematic bias at SNR 500, I think is a huge leap, regardless of the method, and you know will likely be a significant issue, certainly for Lisa.
I think one major issue that especially NR people are kind of worried that will be lacking in 10 years' time is reliable, accurate BNS simulations. And maybe, you know, I've heard about this super resolution method, but I guess I don't expect this to be enough to improve our ability to do BNS to the detail that we'll need for next generation, especially for the post-merger.
Right, we're coming to the end, so in a second I think I'll get Greg up to wrap things up. But we'll do a brief poll before that. Hands up, who's on Team ReLU? Who's on Team SiLU? No one? Bad joke.
Go on. Again, value, anyone who likes values? Vivian likes values. Anyone like sign use? Sell use, gel use?
Yeah,
Who's look at-
they're smoother.
Ah.
They look nicer.
Okay. More layers or wider networks?
I'll be on team no use.
Okay, I'll get Greg up and stop doing these stupid things.
Okay, well, let me say thank you very much to everyone for coming. A massive thank you to all of our panelists, if we can say a big thank you. I very much enjoyed the discussion today. It was a lot of fun. I think I learned a lot and have a few ideas now. There will be a recording of this that is going to be posted to the RAS website. So if you don't want some section, if you've now panicking, thinking I shouldn't have said that, maybe email us. We get the chance to edit the video. So yeah, we'll just blur out Ian and put something over your voice. So yeah, and there's also going to be a write-up of this as well. So that will again be circulated if we can get everyone's email addresses, at least for the panelists. And so again, if there's something you don't want to be said, again, please get in contact with us. So we now have the poster session out there. So please do take time to go and look at people's posters, continue chatting. There is the RAS council meeting, I think, which happens in here at 4. So that's the time you have to get out, unless you want to sit around for the council meeting. Oh, okay, then you're welcome. But if you don't want to join it, then of course don't stay in here. And it's the ANG. Excellent. So with that, I will say thank you everyone for joining. But again, I will say a massive thank you to Anne and Mattia because they really did. All of the organization. All right, thank you all and look forward to chatting to you at some point soon. And thank you everyone online. All right.
How do I get out?
I'll just go through the events over there.